Good morning. Hey, how about that? But this was Castle Bravo, March 1st. The reason I'm using this is because it's a 15 megaton explosion, which is pretty much in the same ballpark as Tunguska, right? So all this nuclear testing we did, there was a huge downside to it, but you know, the upside is it gave us a lot of insight into the power of cosmic impacts. So let me just play this and see what happens. Here we go, yeah. This is the largest bomb ever tested by the United States. This would have been probably the Marshall Islands. So a lot of this is recently declassified within the last 5 to 10 years, I think. Is there anybody in here old enough to remember duck and cover? Yeah. Even when I was like first grade, I knew this is ridiculous. I don't think. And then Sarbamba, which is the largest hydrogen bomb. This is like 50 to 55 megatons. This was the largest hydrogen bomb. Luckily they couldn't use it because it was too big and unwieldy to even transport. But this also is recently declassified footage after, post thawing of the Cold War. Americans were given access to this. So here we go. Impressive. But I wouldn't like that to happen again. Okay, let's go to the net. Let's go on. So comets, a celestial body moving about the sun in an elongated orbit, usually consisting of a central mass, which is the nucleus, surrounded by a misty envelope, the coma, which extends into a stream, the tail, in the direction away from the sun. Now, the tail or the stream is essentially a stream of ionized gas. It's not a debris stream. That's the trail is any debris coming off the comet. And that's different than the tail, which is the ionized gas. So when you see a comet, the tail that you see in the sky is always pointing away from the sun, right? It's taken from the Latin, from the stem cometa, taken from the Greek, which is a modification of cometes, which means long-haired, because ancient peoples looked at a comet in the sky and they pictured a long-haired, probably a woman with long hair streaming behind. So the architecture of the cometary zone in the solar system, we can think now that the solar system doesn't end at Pluto or Neptune. It continues out into the zone of comets. And this kind of is maybe an oversimplified graphic, but it kind of shows you the idea here that the Kuiper belt is generally a flat disk that lays more or less in the plane of the ecliptic, and then the Oort cloud is a much larger zone farther out, almost spherical. So typically the shorter period comets that come into elliptical orbits and that leave a lot of the meteor streams are going to be from the Kuiper disk. They're usually going to be on elliptical orbits. The comets that come in from the Oort cloud are going to generally be on hyperbolic or parabolic orbits, which means the geometry is open. They don't, they come in, they make their passage around the sun, and assuming that they never return. Originally, the Taurid meteor stream, or the comet Encke, was believed to be on a parabolic orbit, but then was later discovered by Fred Whipple to be on an elliptical orbit. And here's another graphic, kind of like this graphic. Oh, I'm looking down here, yeah. So here you can kind of see again a rendering of the Oort cloud, the spherical Oort cloud, and the Kuiper disk, which is the zone of comets. Call it a reservoir. So just some interesting photography here. You can see Comet Hale-Bopp, and you can see there the blue coming off, that's the plasma tail, the ionized gas coming off as the comet nucleus is devolatilizing. And Hyakutake, so the interesting thing I found about Hyakutake was the spectral analysis showed that there were high concentrations of acetylene gas in the nucleus, along with methane and ethane, which are, of course, highly flammable gases. And Comet Swan, discovered March 25th, 2020, by the Solar Wind Anisotopic Topies camera, discharging an estimated 2,866 pounds of water every second. Oort cloud in origin. So we probably won't be seeing Comet Swan again. Comet West, early 1976. And there's Hyakutake again, very long streamer of a tail. Now and here's Comet Machholz passing right in front of the Pleiades. And then this is just showing, this would be a comet linear, which is, its orbit is highly tilted to the plane of the ecliptic. So it's going to be less likely to be an impactor at any point, because generally it's going to be the comets that are laying close to the plane of the ecliptic that discharge debris that the Earth could potentially encounter. And Comet Atlas, you see there's a huge inclination there of 139 degrees. So again, this one's on a parabolic orbit. Yeah, Oort cloud comet, discovered the 9th of January 2023. And again, there you can see the distinct difference between the two tails, or the trail and the tail. Okay, so after the last passage of Comet Halley in 86, we kind of came up with a new model of a cometary nucleus, which essentially it's almost like an egg that, if you look at a cutaway, it could be an icy matrix with any number of various materials entrained within it. And, once a comet begins to come into the inner solar system, into the zone of the planets, it begins to heat up, it begins to devolatilize. It'll come in typically, often depending on perihelion passage, which is its closest passage to the sun, it'll oftentimes begin to undergo a process of disintegration. And when it does that, it gives birth to meteor streams. And then the Earth crosses meteor streams regularly. There's probably a dozen of them or so every year that the Earth crosses. Some are more spectacular than others. I always have liked the Draconids and the Geminids and the Leonids. I like the Leonids because they're come out in the fall when you can see them very nicely. The Taurids, we cross the Taurid stream twice each year, once in late October, early November. They have sometimes been called the Halloween meteors. And I did a whole presentation on that I think is online about the origins of Halloween and its possible connection with the Taurid meteor stream. And then we cross again in the spring, late June, early July, not spring, summer, late June, early July. And this is perhaps the origin of the Tunguska object. I mean, I don't think it's been proven one way or another, but the timing was certainly correct, and I'll show you in a slide coming up. Its position, its radiant point in the sky that it came from, which is fairly consistent with where a Taurid meteor would be coming from on June 30th. Now, I would mention, by the way, that the Halley-type nucleus, this I think, the Halley nucleus is maybe 10 miles or so along the long axis. So an object like this disintegrating could potentially produce, many thousands of Tunguska-sized objects. And luckily, what it seems is that, like, the Taurid meteor stream seems to be very dispersed. It's also wide, very wide. It takes several weeks to cross, which means that it's probably an old meteor stream because it's had plenty of time to become diffused along its orbit. A young meteor stream, which has just been produced by the disintegration of a comet, is going to be it's going to be clumped in certain areas because it hasn't dispersed yet around the meteor stream. Every trip around the sun, that material is going to become more dispersed, and eventually it'll become uniformly distributed more or less along the path of its orbit. But if it's an old one, it's going to be already dispersed, and that's pretty much what we see with the Taurid stream. If it's younger, it's going to be perhaps areas where the amount of the meteors are going to be more concentrated. And after Shoemaker-Levy 9, which how many of you remember that? Right? Shoemaker-Levy 9 was interesting because named after Gene Shoemaker and Carolyn Shoemaker and David Levy, who sort of co-discovered it. When it was first observed, it was just emerging from its para-Jovian, if you want to call it that way, passage. It had swung by Jupiter, and it had apparently passed within the Roche limit of Jupiter's gravity field, where the gravity of Jupiter was strong enough to overcome the cohesiveness of the nucleus, so it began to disaggregate. And so as it's coming around Jupiter and was discovered, it was already beginning to disassemble into 21 individual nuclei. And I think it was about 3 months of observations, the astronomers were able to calculate the orbit, pretty much. You use what's called the orbital elements. And the orbital elements were, you have to know, you have the timing, you have to know the geometry of the ellipse, you have to know the inclination, and there's other factors. I'm not going to try to explain that right now, but after about 3 months of observation, they were able to project its orbit a year or so, about a year or more into the future, and then realize that when it crossed the Jovian orbit again, it was going to be crossing precisely at the point that Jupiter was going to be occupying. Now, what I suggest happened was that, the Shoemaker had been moving in an orbit, a Jovian orbit, and had probably made multiple passes between the Sun and Jupiter, and on each pass got progressively closer to Jupiter itself, being drawn in by Jupiter's gravity field, and then it eventually, the orbits intersected. And we witnessed in the second week of July in 1994, 21 pieces of the original nucleus plunge into the Jovian atmosphere with pretty impressive results. And after that, I think there was a more of an interest in looking at evidence of multiple impact events, and these are called CATENA, I think that's the proper pronunciation, or CATENA, it's spelled C-A-T-E-N-A, which are these, like apparently where you have this would have been an object that broke up, had not had time to disperse along its orbital path, and so when it struck the surface of this, as I believe this one's on the moon, it was almost like a rapid machine gun fire. And I think Robert Schoch would say that this was probably a plasma discharge. I'm more inclined to believe that it was a multiple impact event. And I will just say that I think there's a lot of merit to what Robert's doing, but I think that, we know that impacts occur. We know that there's all kinds of debris out there in space. So I'm of the mind that, yes, we should absolutely consider the sun as a major factor. And there is evidence, like he showed yesterday, there's evidence that the sun, I think, does go through hyperactive phases, but at the same time, I don't dismiss the impact phenomena as being, in my mind, is still the dominant effect. For example, Meteor crater, which I interpret to be an impact. I've been there many times, and there is remnants of the iron asteroid, the iron meteorite that impacted there. I mean, you actually have a piece sitting in the museum there. It's really heavy. I tried to make off with it, but it was completely impossible. It was way too heavy. And there's multiple examples of this, mostly on Mars, on the moon, but several of the Jovian planets, moons have these catena on them as well. And I think that maybe we should consider, and I think I have a slide showing this in here that'll be coming up, that perhaps an impact encounter on Earth may have involved a catena like this. There's an array of craters across central U.S. They're not all proven to be craters, but enough of them are now, I think about 4 of them are definitely proven to be craters. And they're more or less in an alignment. I think at the 37th or 30th, I think it's 38th parallel, moving more or less from east to west. And I think I have a slide of that coming up here. So you can see there's quite a few examples. Once we really started looking, these things show up, and they look like, again, Shoemaker-Levy 9, by the time it hit Jupiter, the pieces had become pretty well spread out. So it took almost a full week for all 21 pieces to plunge into the Jovian atmosphere. But these look like, you've got an object that was just probably tidally broken up, shortly before impact. So just a few comets in the process of disintegrating. So comets Schwarzman-Lachmann. Everybody say that really quickly 3 times in a row. Okay, that'll do. So here's a close-up. You can see that it's fragmenting into multiple pieces, and this is the standard life cycle of a comet. At some point, when they're out there in the Kuiper disk or the Oort cloud, it's almost like they're in deep freeze hibernation, and something has to trigger. I think something would trigger them to begin their journey sunward. I don't know exactly what that would be. Stephen, do you have any thoughts on that? Okay. Well, but something, we have to agree, something will dislodge them from the equilibrium of their orbits, possibly even sending them further out or sending them sunward. And once they go sunward, then they begin to undergo, well, first of all, it's almost like you switch on the ignition, they come alive. That's the first thing they do. They begin outgassing, they begin devolatilizing, and then with enough passages, they'll eventually disintegrate. And I think the final end result is that they could literally turn into streams of dust. I introduced the idea yesterday of the Kreutz family of sun grazers and the sun divers. I showed one video of a sun diver falling into the sun, which was interesting because just maybe, I think most of the commentary I've seen on it said, well, it was just a coincidence that there was a giant solar outburst in the moment after. But I noticed that the solar outbursts seemed to occur on the antipode of the impact point. So I'm wondering if there could have been some kind of I've actually seen it, I'll be pulling some of this up to look at, talking about sunquakes that are connected to the infall of some of the sun-diving comets. So a lot of this is new that we didn't know 20 years ago, but 25 years ago, but with the deployment of solar observing satellites, we're learning a whole lot more about the sun than we used to. And I think that the Kreutz family of sun grazers was not even discovered until maybe it was the SOHO, the Solar Heliospheric Telescope that was trained on the sun, that we discovered a whole other family of comets. Comet Linear, here you can see two stages of its disintegration. And so comets begin as a single nucleus, and then they disintegrate. They end up in meteor streams. Those meteor streams can produce dust. Then that dust can either continue to become part of the, one of the ideas is it's the source of the zodiacal light. Other possibilities are that it's swept up by planets, or its most likely fate is it's going to fall into the sun or get swept into the sun. So here's your second generation disintegration of comet Schwarzmann-Wachmann, fragment B, photographed by Hubble Space Telescope, April 18th, 2006. So I think you see the original progenitor nucleus up there on the top, followed by this material that's disintegrating. Now within that trail of stuff there, I mean, there could be some extremely large stuff that could, be ranked as a planetary killer. And then who knows how much smaller stuff. Now the Tunguska object of 1908, that would be on the very small end of the spectrum. And remember, we talked about Chelyabinsk. That was, I think, around 50 to 60 feet in diameter, about 1/3 the estimated diameter of Tunguska. But, the energy the volume is going to scale according to the cube of the radius. So you can do the math on that. You'll find that the Tunguska object, even though it's 3 times larger in diameter, it's going to be many times greater in volume, and then presumably also in energy, kinetic energy released at the moment of impact. Now, of course, the Tunguska, the studies I've seen most recently suggest it was quite a low density object, which again is consistent with a comet, piece of a comet. And it's going to have a different atmospheric effect, let's say, than a high density asteroid, iron asteroid, encountering the Earth. So you've got, on the one end, you've got maybe almost the density about 1 gram per cubic centimeter, which is going to be the density of water, or, almost like a snowball. On the other end, you've almost got more like cast iron, and then you've got your carbonaceous meteors right almost in the middle that are basically about the same density as a typical rock you would pick up, 3.5 grams per cubic centimeter. And so they're all going to have different effects. Typically the object that struck and created the big hole in Arizona at Meteor Crater. How many of you guys have been to Meteor Crater? Okay, I've done 3 or 4 tours now in the Southwest, and that's always on one of our stops. Meteor Crater was an iron asteroid, and it plunges all the way through the atmosphere and strikes the ground. Tunguska, as I was talking about yesterday, did not strike the ground. It blew up in the atmosphere. And that's a function of the density. But it's also going to be a function of the angle of approach. You can picture that an object coming in vertically is going to have to pass through a much thinner layer of atmosphere than one coming in at a very oblique angle, which now has to pass through a lot more atmosphere. So it's also a function of the angle at which it impacts. So you've got multiple variables that are going to affect the outcome: the density and composition of the object, the angle of approach, the composition of the target rock. Also, for example, it's going to have a different effect if it plunges into limestone, which is going to release a lot of carbon dioxide, as, say, for example, if it plunges into basalt or granite bedrock. Obviously, it's going to have a very much different effect if it plunges into an ocean rather than into the earth. And then you're going to get an enormous injection of water vapor into the atmosphere that would then rain out. It would also generate tsunamis. So, if you have a 0.5 kilometer object plunging into any of the global oceans, all of the coastal areas are going to be affected by very large tsunamis. And I haven't looked at the studies recently, but I mean, we could be talking about tsunamis that are, several hundred feet at height when they make landfall. And if you recall, if you have ever seen any of the videos from the tsunami of 2004 and the more recent one in Japan, they're pretty impressive. And those you're looking at, I think, maximum wave height at landfall around 50 to 60 feet. Generally more around 20 feet, but you can, if you've seen some of those videos, if you haven't, you can go online and see some of those, and you'll see the power of a tsunami and the power of moving water. And we'll be looking at some of the landscape effects of the power of moving water shortly. So let's keep going here. So this is again showing, here you can see here how each of the nuclei, it's essentially become multiple nuclei, each one with its own plasma tail. And there's your string of pearls. This was a photograph of Shoemaker Levy 9, the Cometary debris chain. And this is an artist's depiction of its approach to Jupiter. And over that week, 21 pieces fell into the Jovian atmosphere and created these gigantic plumes that were larger than the Earth itself. And I think that was a point in the history of our study of the denizens of the deep, as I like to call them, or a lot of, I think, scientists, astronomers, and others, even geologists across the spectrum, begin to take the idea of cosmic impact more seriously. Because, nobody expected this. I remember Gene Shoemaker quote from the late Gene Shoemaker, that this was like a once-in-a-lifetime event, or a once-in-a-millennium event. I don't remember exactly. I think it was that once-in-a-millennium event. But since we've only seen this happen actually in real time once, that's not enough to make any kind of statistical conclusion from as to frequency or periodicity of such an event. And I brought this up yesterday. We know that Tunguska event, say compared, I like to use this comparison between Meteor crater and Tunguska, because Meteor crater leaves a scar. It's estimated to be around 50,000 years old. So 50,000 years ago, an iron asteroid slammed into the deserts of if it was, probably was not a desert then. I think, if I recall, it was not a desert at that time. But in any case, it slams into the Earth and leaves a big crater that we can come by thousands of years later, see it in the ground, and here's the mute evidence of this catastrophic event, right? Well, Tunguska, if we did not know about it, a few centuries after the effect, if it had happened a century earlier, we would not have known about it. Simply because, the story of Coulee and his intrepid efforts to track down the zone of destruction caused by the Tunguska event, in I think it was between 1927 and 1928, when he was finally able to access the site. And as a result of that, it was already, he was able to see the blowdown of the trees, as far as the eye could see. But even now, it's rapidly regenerating, and in another century or two, it'll be very difficult, except to the trained eye, that there had ever been something like that happened. Well, if you look at the census of the things that could strike the Earth, the low density stuff is really a lot more prevalent than the things that. So it suggests that a Tunguska type event may be considerably more prevalent than the kind of event that leaves a crater. So if we do crater counting in our conclusions about the frequency of Earth impacts, which to me would include atmospheric impacts, may be off, may be too low. Because certainly a Tunguska event, as I showed you, I played Castle Bravo to just give you an idea of what a 15 megaton explosion looks like. And the kinetic energy released by Tunguska was considered to be in that range. Now, I've seen it from 5 up to like 40 megatons. So I'm taking kind of a little bit on the conservative side towards the low end, but they're even there at a 15 megaton. A 15 megaton explosion on any urban area in the world is going to completely destroy that urban area. And if Tunguska had happened over a populated area instead of the remote taiga forest of Siberia, it probably would have completely altered 20th century history. I made the point about Chelyabinsk, which happened on February 15th, 2013. It was, was much smaller than Tunguska, yet it damaged over 7,000 buildings and caused over 1,500 injuries. Now, if it had been just slightly larger or slightly denser or coming in at a slightly steeper angle, it could have caused quite a few casualties. And then it maybe would have seen, at this point, among most people was very much in the news. It was very much talked about at the time in the immediate aftermath. Excuse me. But now it's, for the most part, forgotten. Nobody's considering that anymore. But again, it was like, to me, it's like a wake-up call. Hey, these things are out there. They, Earth encounters them with a far greater frequency than anybody had imagined. But also, if you're paying attention, one of the things is that, took over a century and a half to discover the first 4 asteroids. And now we've discovered, every few months, one comes flying into near-Earth space. Now, I say near-Earth space, I don't mean like within the atmosphere, although several of them recently have come within the zone of communication satellites. So that's pretty darn close. Now, luckily, they were, for the most part, relatively small, but we've also seen some pretty darn big ones coming, pretty close. I mean, certainly close in the cosmic sense. So these things are out there. So this is kind of how I've broken down the 5 stages in the life cycle of a comet. I call aggregation is that first phase. Now the original zone of comets, generally the idea is, and I have no reason to question that, it's essentially the leftovers from the creation of the solar system and the planets, right? That's what I'm calling aggregation. Then hibernation, they're going to be out there in their zone, in their reservoir, there's like the Kuiper disk is slowly rotating, right? It's sort of a coherent system, slowly rotating about the sun, and it's in a quasi-stable orbit, so that a very small perturbation can cause it to migrate either further out or in, but in that region of space, there's generally not going to be a lot of effects that are going to cause it to dislodge, but there are. That's the thing that I'm very curious about. If we can at some point see what the triggers are, perhaps something on a galactic level. Now this is pure speculation. Perhaps something energy being released from the galactic nucleus. Perhaps the passage of a large object like a star. One theory that I've seen that's kind of interesting is conjunctions of the outer planets may be able to, and I think I've got something on those studies that were done maybe 15 or 20 years ago might be enough. If those, say the comets in the Kuiper disk are moving slowly, if you can accelerate them, if some gravitational force can pull them and accelerate them, they're going to migrate outwards. If you can slow them down or almost like put the brakes on, they will then migrate inwards. And that could be the beginning of a process of transferring those comets from the disk outside of Neptune into the inner solar system. So once they're, whatever the process is that causes that, that's what I'm calling activation. So now, once they start their sunward journey, they come alive. They start outgassing, they start devolatilizing, and then eventually they're going to disintegrate, as we've just seen. And then I call amalgamation. This is where they are actually swept up by planets or the sun, and that would be the final stage in the life cycle of a comet. Is it ends up being dust, which is going to also be aggregated to a planet through gravitational attraction or drawn into the sun. Or the nucleus, just like we've seen from some of the sun glaciers. What we've seen through solar observing satellites is the comet will come making perihelion passage. It'll disappear behind the sun, but then it never reemerges. So the assumption is that it's swallowed up by the sun. So a little bit of elaboration. Aggregation is the accretion of interstellar matter, condensation, integration, ejection from the inner solar system, and I like this metaphor, the stone the builders rejected. Of course, it's a biblical reference, but if you're into that kind of thing, I find it sort of appropriate in its own way, and this is the reservoir formation. Hibernation is your deep freeze in the Oort cloud or the Kuiper disk. Activation is perturbation, orbital transfer, sunward journey, outgassing, tail formation, transformation to a devolatilized nuclei. And then the disintegration is going to be a vaporization of the ice matrix, formation of meteor and dust streams after successive orbits, and finally amalgamation, which is going to be your solar and planetary encounters, crater formation, raw material injection to Earth's atmosphere, hydrosphere, lithosphere, biosphere, and as a possibly or likely a primary stimulus to extinction and evolution cycles. So meteor streams, just a little bit of the nomenclature here. This is a nice little graphic. It shows you the perspective. If you go out and you're watching a meteor stream, you'll always know like the radiant point. And the radiant point is going to be targeted on a specific star field, right? If it's and since all the stars are constellations, whatever that radiant point is targeted upon, that gives its name to the meteor stream. So as you can see here, the X that you see up there to the right, that could be, like, let's say if it's the Taurids, that X is going to be almost superimposed right on the Pleiades star cluster, right? And so Pleiades traditionally is the shoulder of the bull, Taurus the bull. And so from Taurus the bull, we get the name, the Taurid meteor shower, right? And just showing the perspective effect of below with the highway, looking at the telephone lines and stuff, because when you're looking up into a meteor stream, you almost have to visualize you're looking up into a tunnel, and this stuff is flying out from that point, and that's why it's called the radiant point. It's because the material is flying out from that point, and if you go and it's a really heavy meteor shower, you really can get that perspective effect. And I've only seen a couple of those. Some of the ones I've read about, like that I'll show you some slides about here, must have been just mind-bogglingly awesome to the witnesses. And so here's a time-lapse photo of the Leonid meteor shower, clearly showing the radiant, right? So you can see the star paths are the things going from upper left to lower right. But then if you look at and I don't have a pointer here, so I can't, but I think you can see the streaks of light that are, if you follow them back, they're going to converge more or less in the center of the screen. If I had can you see that? Can you make that out? Good, okay. And this was a Leonid fireball. The Leonid stream has produced some pretty impressive fireballs that have been seen by folks. The interesting thing about this is that you actually look at it, you can see the main fireball has got a little companion. You can see up there to the upper right, that little streak. So it actually is a main piece of the Leonid meteors, and then it's got a much smaller one that's accompanying it in. Now this thing burned up in the atmosphere. It didn't strike the Earth. Okay, so here, this was, I think, a woodcut, and you see these people are all out of their homes. This was, I forget the year, but I think I've got it on the next slide, but they're all out, you see they're all looking up in the sky, and the next one actually shows the rest of the woodcut here, what they were seeing. Now, you can see why I'd say I'd love to see something like that. Okay, there it was, November 13th, 1833. So the peak of the Leonids is usually around the 17th of November. But yeah, I remember reading the accounts of these. A lot of these people who came out and saw this thought this was it. This was the end of the world right here. These days we'd know it probably wasn't the end of the world, and they could enjoy the spectacular awesomeness of something like this. So again, this is what this is showing us, is that that the meteorite debris is not uniformly distributed throughout its orbit. So we might cross the orbit, the Earth might cross the orbit of the Leonid stream at some point where there's rather low population, but then at another time it might pass through the stream when there's a really a cluster, and that's what happened here in 1833. And this was another representation of it from seen out in the Atlantic Ocean. So here are your selected meteor streams with data. So you've got the name of the stream on the left, and then the comet associated with it, because most of them have comets associated with them. So, and your date of the peak. So you've got your quadrant quadrantids, the Lyrids, the Eta Aquarids, which are connected with Halley's Comet, the Perseids, which is associated with Comet Swift-Tuttle, and the Perseids is the one that you can get out and see in the summer. I've oftentimes tried to time some of my tours out west in the western states to coincide with the Perseid stream, because it's sometimes can be a pretty impressive stream, and it's nice to be out in the desert or in the clear air of the high elevations of some of the western states. You can get some pretty impressive effects, like you might see one really good blazing meteor like every minute or two, sometimes 3 or 4 within a minute. The Draconids, which notice the date there, October 7th through 9th, the radiant is in the head of Draco, as you might guess. That's why they're called the Draconids. They were a very impressive performer a few centuries ago, and there's many stories about people being blown away by the intensity of a Draconid meteor shower. Not literally blown away, but psychologically blown away. Okay, the Taurids, which are associated with Comet Encke, early November peaks. They have been referred to as the Halloween meteors, because they actually do peak right around Halloween, All Saints, and All Souls Day. And I've made the conjecture that in times past, the Halloween observation was actually associated with this particular meteor stream, and the possibility that there were encounters with more macro-sized pieces of the Taurid meteor stream that could have caused severe consequences for people in the past. There's a whole group, Victor Klube, William Asher, William Napier, and a group of others. I call them the neo-catastrophists, that have been studying and publishing about the Taurid meteor stream for years. William Napier has written a paper suggesting that the encounter, the lower Younger Dryas boundary, may have been triggered by an encounter with the Taurid stream. And then the Leonids, as it says there, radiant in Leo, they peak around November 17th. They can be an impressive performer as well. Of course, it's also getting fairly cold in November, so if you're going out in November to try to witness the Leonids, make sure you dress warm. But I would highly recommend taking a note of the Perseids and trying to be somewhere out, during that period from August 12th to August 15th. Comet Swift-Tuttle is associated with, and also comets. It's a prominent stream that has frequent fireballs, and I've seen some really breathtaking fireballs out, watching that stream. So make a note of that. And then finally, the Geminids, I've got a question mark there because we're not sure, 3200 Phaeton, whether that is the associated comet or not. Leonids is associated with Tempel-Tuttle. Now let me go back to the Taurids for a minute and say that it's associated with Comet Encke. Encke is part of that stream, but that was probably not the original progenitor comet. Encke is probably a sub-comet, if you will. That there's also another comet associated with that called Rudnicki, and it's likely that they are pieces of the original very large comet that came into the inner solar system. The estimates I've seen are 25 to 30,000 years ago at some point. I've noticed, interestingly, that there was a major climatic shift around 26 to 27,000 years ago, which geologists and paleontologists and paleoclimatologists have looked at and have referred to as the onset of the late Wisconsin phase of the longer Wisconsin Ice Age, which followed in the aftermath of the Eemian or marine isotope stage 5e, which I mentioned yesterday, which lasted from about 116,000 to 129,000 years ago, which is often considered to be the closest parallel to our own Holocene epoch. It was a period of, it was the warmest period that we know of within the last couple of 100,000 years at least, and it was warmer than now. In fact, a lot of sea level studies, I've just got a on my podcast, Squaring the Circle, I've done a two-parter on sea levels from the past, and I've kind of focused in on the Eemian because there's evidence of sea levels 20 to 30 feet higher than now, and also evidence of perhaps a 50% deglaciation of Greenland. And that Greenland was actually quite verdant during the Eemian and probably would have been very conducive to settlement and agriculture and so on. Also, the latitude belt at which the tundra shifted far to the north. In fact, most of the tundra was pretty much gone during the Eemian. That I would now probably concur with Robert on this, that the Eemian was the result of a period of active sun. And so anyways, we'll maybe come back to the excuse me, the Eemian. It's double E-M-I-A-N, Eemian. Write it down, look it up. It's a very interesting period of Earth history. We now know that modern humans were around during that time, and I think that would be a very I think we're just really kind of like, almost as far as with the Eemian, we're kind of like where we were at maybe 20 years ago with the Younger Dryas. And I know when I first started talking about the Younger Dryas, nobody had ever heard of it except a few. It was in scientific papers. I'm sure, some of the folks that were involved in the early publications, in the 2000s and stuff were aware of it. But it was pretty much an exclusive province of people that knew what the Younger Dryas even was. I discovered it maybe in the 80s when some of the early studies were first coming out, when they were realizing, without connecting it with any cosmic event. I'll point that out. For at least a couple of decades of research, there was no connection with a possible cosmic event. But yeah, it was the polar wildflower Dryas octopetala that gave its name to the Younger Dryas. The Younger Dryas implies that there was also an older Dryas. So the older Dryas, I think, was right there leading up to about 14,600 years ago. Then there was a period called the Balling, and then the Alarod. There was let me see, I'm trying to remember, maybe the Younger Dryas came between it, the older Dryas came between the two, but I think it was before. Anyways, there was that warming period that led up to the Younger Dryas that was consistent, I think was consistent with Milankovitch forces, which is orbital changes, geometric changes in the orbital relationship of Earth to Sun. And those forces are generally going to be very slow acting. The problem is that you seem to have a period of warming, rather gentle warming, that occurred between, say, 14,600 and 15,000 years ago, and then the lower Younger Dryas boundary. That seems consistent with Milankovitch. But then you get to that Younger Dryas boundary, and then something happens with extreme rapidity, and this is the boundary at which the impact proxies are being found. I don't know of anybody other than Robert that has suggested that those are not impact produced. He said that you could produce those with solar events. I haven't looked at any of that research, so I have no opinion on it. He's probably right in some cases, but there's been such a wealth of research done on the impact proxies, the microspherules, the magnetic grains, the iridium, the platinum, the shocked quartz particularly, all these things that have been associated with, in one way or another, with the lower Younger Dryas boundary, that I definitely come down on the side of a cosmic impact. However, I'm open to the idea of considering a significant solar role, and do believe that we probably have to be thinking in a grander scheme of things, where we're kind of looking at a unifying process. And I showed the video yesterday. I can show it again today, of that connection between the sun diver and that amazing solar outburst that occurred at that moment. And we'll quote from some stuff here later, maybe this afternoon when we have part 2 of this. We'll quote with some stuff that suggests that this could be a factor, that the solar stability might be connected with the infall of cometary masses. Again, probably the standard response to that would be, well, a comet nucleus falling into the sun would be too small to have a significant solar effect. But you don't know, because there's potential feedbacks, and again, maybe it could be that there has to be certain conditions that would be conducive to a significant solar response. Maybe that those conditions don't always prevail all the time. So I don't know. Again, this is kind of new area for me to study and research, and I find it very fascinating to think that there could be this integrative process that between the influx of cometary debris into the solar system, possibly related to a heightened solar response, but I'm not going to give any definitive opinions on it until I've learned more. And then just a few accounts that I always like, eyewitness accounts of things. This was a May 30th, 1911. And it says here, about 7 o'clock p.m., the 30th of last May, I was standing in my yard facing west when a brilliant meteor caught my eye, which I will try to describe, though no words can carry any adequate picture of it to one who did not see it. It consisted distinctly of a head or nucleus and a long tail. The head, about 3 or 4 times the apparent diameter of the sun, showed a mass of intensely brilliant streaks and patches of color, much like the effect of a bursting sky rocket. This stately meteoric train, steadily moving with perhaps 1/4 the angular velocity of a shooting star, spurning both earth and sky and aimed at some unknown faraway point in space, and never to be repeated in the experience of one lifetime, will remain as long as earthly memory survives, the most striking emblem of the majestic. Yeah, I like that. If you ever read these accounts from, the 18th and 19th centuries, they seem so erudite. And it's, you find out, it's some farmer standing out in his field. And yes, the extraordinary meteoric display of 1913. This was published in the Journal of the British Astronomical Association. At about 9:05 p.m., this is at night, on the 9th of February, 1913, there suddenly appeared in the northwestern sky a fiery red body, which quickly grew larger as it came nearer, and which was then seen to be followed by a long tail. To some observers, the tail seemed like the glare from the open door of a furnace. To others, it was like the illumination from a searchlight. To others, like the stream of sparks blown away from a burning chimney by a strong wind. The body moved forward on a perfectly horizontal path with peculiar, majestic, dignified deliberation, and continuing its course, it moved on to the southeast, where it disappeared in the distance. Before the astonishment aroused by this first meteor had subsided, other bodies were seen coming from the northwest, emerging from precisely the same place as the first one. Onward they moved at the same deliberate pace, in 2s and 3s, with tails streaming behind. They all traversed the same path and headed for the same point in the southeast. Gradually the bodies became smaller, until the last ones were but red sparks, some of which were snuffed out before they reached their destination. As to the number of bodies, there was a great diversity of statement. The usual estimate was from 15 to 20. Some said 60 to 100, while others said there were thousands. The entire time occupied by the display was about 3 minutes. Now, if you've ever seen shooting stars, you know that they just last for moments, a second, a few seconds. So to see something lasting 3 minutes, that would be pretty damn impressive. Just as the bodies were vanishing, there was heard in many places a rumbling sound like distant thunder. The stretch of country over which the display was seen is unprecedented. In the present case, persons dwelling 2,500 miles apart saw the same bodies. Moreover, the descriptions furnished by observers in Bermuda, in Ontario, and in Saskatchewan do not materially differ. Got that? Saskatchewan, Ontario, Bermuda. Now this is interesting. Observations of the size of the bodies were very discordant, but there is sufficient evidence to show that they were of considerable size. Several observers considered the leading body to have a diameter equal to that of the full moon, or nearly so. One observer estimated the diameter at half that of the full moon, and another at 1/15 of the moon's diameter. The last estimate gives a real diameter of 123 feet. The largest bodies were probably at least 100 feet in diameter. The tail of the largest meteor is estimated to have been 39 miles long. Now, let's just stop for a minute and consider that. 123 feet, now you're getting into a Tunguska-sized object. If there were multiple objects at least 100 feet in diameter, you're talking about objects which, if they penetrated the atmosphere to a low enough altitude, would detonate, just like Tunguska did, right? I think we've got here's a painting by Gustav Hahn of the Great Meteor Procession of 1913. And notice how it's going more or less parallel to the horizon. So what most likely happened was an object was captured into a geocentric orbit, and it traversed probably half the planet while it was disintegrating. But it was captured in such a way that its orbit, its pathway was tangential to the Earth. Had it been slightly steeper tilted, now it could have been very interesting consequences. Here's the path of the Great Meteor Procession. If you can see up there at the upper left in Saskatchewan, coming down over Manitoba, if you get down there over the Great Lakes, you'll see that it is passing right over New York State, passing over Boston, New York, that area. You can see it's passing right between Lake Ontario and Lake Erie. Now, if you had multiple objects in that stream that were the size of the Tunguska object, and this thing was just a little bit more oblique to its entry into the Earth's atmosphere, imagine what could have been different. If this thing in 1913 had come in with multiple Tunguska-sized impacts over the Northeast, over the areas of New York, Philadelphia, Boston, and Toronto, Montreal, that could have been a major historical event. The outcome of the 20th century could have been very different if that had happened. But as it was, it just provided a very spectacular visual experience for the people who witnessed it. But other than that, it was harmless. This maybe wasn't quite a cosmic catastrophe. This was an object about the size of Chelyabinsk, sort of making a glancing blow. I think this was in 76, I believe. It sort of made almost like, imagine a stone skipping off the water. It came in again at a very tangential angle to the Earth at that point, and it essentially just skipped off the atmosphere. But if it had been coming in at a slightly more oblique angle, I don't think nobody would have been killed, but it would have made a heck of an event. It would have been, like I said, similar to Chelyabinsk. Then we'll get a little bit into the Taurid meteor stream. This is Victor Klube here, and this is from the book, The Mass Extinction Debates, How Science Works in a Crisis, 1994. I'm going to go down to about the fifth line there that I've got underlined. He says, thus a large circumsolar stream of cometary asteroidal material intersecting the Earth's orbit, previously only suspected in modern times, has now been confirmed in sub-Jovian space. Streams of this kind containing both active and inactive cometary debris are a natural consequence of the breakup under the influence of the sun's radiation field of very large comets of heterogeneous composition. So this is pretty much, again, focusing on the Taurid stream, which, according to this school of thought, played a much more prominent role in history than has heretofore been recognized. I'm going to show you here the orbits of the Taurid meteors. There was the work of Fred Whipple, who did the first photographic study of the Taurids back in the 1940s. This is even earlier than that, the 1937. You'll notice the date here, October 31st, November 10th. Now what we have here is we have the two yellow ellipses. You can see there you've got the sun, that's obvious what that is. And then you've got the orbit of Mercury is the first white circle, orbit of Venus is the second, and the orbit of the Earth is the third. And you'll see in there the green arrows are showing you all the movement, and you'll see that the green arrow showing the Earth moving counterclockwise. It's showing the meteor stream moving counterclockwise. Now, you see there you have number 712 and number 697. What this is for this particular graph, I chose two meteor positions, orbital positions, that sort of define the more or less the outer limits of you can see there from October 31st to November 10th. So you've got, not quite 2 weeks apart. So what we're seeing there is kind of a definition of the outer limits of the particular stream. Now go to the next slide. And you'll see here that, again, if you're looking at this, follow the Earth around, and you'll see where it says June 30th. Okay, so around June 30th, the Earth is crossing the stream, and you'll see that the stream has just made its perihelion passage. In other words, its closest passage to the sun. So it's coming around the sun, and we don't really see, as a rule, we don't see the summertime Taurids because of the fact that to see them you would have to look in the direction of the sun, right? So the light of the sun blots them out. But follow the orbit of the Earth around counterclockwise until you cross the stream again on November 1st. Now, again, if you look at the green arrows are showing the orbital direction of the Taurid stream. So what you see there is that during on November 1st, or let's say around Halloween, if you're looking up towards the radiant point of the Taurid stream, you're looking away from the sun, and in fact, you're looking almost dead on targeting the Pleiades, the shoulder of the bull. Is this making sense? So you can see how the Earth crosses the stream twice. We generally don't see it during the summertime Taurids, but we do see it during the fall Taurids. And what was the date of the Tunguska event? June 30th. So June 30th is right there pretty much prominently in the middle of the summertime Taurids. Also, I'll show you in a minute here where the radiant point coming out of the sky was of the Tunguska based upon the collection of several hundred eyewitness accounts. And it puts it very close to the sun. So its position in the sky and its timing was both consistent with being a member of the Taurid stream. Now, this does not prove that it was a member of the Taurid stream, but it makes it a highly circumstantial case that it was. So going back to Coulee and Napier again, the long evolution of the Earth then is distinguished by a relatively steady evolution superimposed on which are rapid, sometimes overwhelming changes, whether in the evolution of life or mountain building or even disturbances in the core itself. Many geologists over the years have voiced the suspicion that these changes have a galactic periodicity and have speculated that somehow the galaxy is affecting the affairs of Earth. What was lacking in all these speculations was a mechanism for inducing the galactic periodicities, and it was not until the late 1970s with the discovery of the molecular cloud and Apollo asteroid systems that the mechanism was discovered. There are two main causative links in the chain connecting the galaxy and the Earth. The first of these is the ebb and flow of the galactic tide, which we have seen is reflected in the ebb and flow of comets into the interplanetary system. The second link is the existence of giant comets. Rare though they are, it is the giant comets which contain the bulk of the mass which enters the planetary system, and it is their disintegration products which interact most strongly and directly with the Earth. As we have seen, the breakup of a very large comet will produce a wide range of debris from objects 10 kilometers across to probably hundreds of kilometer-sized bodies to temporary swarms of sub-kilometer objects down to dust, in quantities sufficient to block the path of sunlight. We now ask, how would the Earth machine respond to the influx of such material? Between the 3rd and 15th of November each year, the Earth runs through a meteor stream coming from a small area in the constellation of Taurus the Bull. A young stream made up of meteors not long released from their parent comet would be narrow and probably strong, and the Earth would pass through it in a half a day or so. The Geminid meteor stream is one such, the Earth encountering it on the 10th of December each year, and the shower being over by the 12th of December. The Taurid meteor stream, on the other hand, takes the Earth 12 days to cross, and it is not very intense. It looks old. It has two main branches, northern and southern, emerging from slightly different parts of the constellation, the branches being about equal intensity. Orbiting the Taurid with the Taurid meteor stream is a small comet discovered in 1818 by Pons. An orbit was calculated for this comet by Johann Encke, a pupil of the famous mathematician Gauss, who had developed a method for calculating the orbits of bodies from their movement across the sky. There are about 100 known short-period comets. All of these, with the sole exception of Encke's comet, are in orbits which sooner or later lead to a close encounter with Jupiter and ejection from the solar system by the powerful gravitational pull of that planet. But Encke's comet has somehow established itself in a stable orbit such that it never comes within the Jovian sphere of influence. It does, however, come close to Earth. In addition, now this is where I think it gets interesting, there may be 1,000 or 2,000 asteroids over a kilometer across in orbits which make them a potential collision hazard with the Earth. None is more than about 10 kilometers across. Their surface is extremely dark, and fewer than 50 have been discovered. They are known as Apollo asteroids, after the prototype discovered in 1932. Encke's comet is in fact the sole example of an active comet in an Apollo orbit. The orbit is highly elongated, and the comet may approach to within 0.34 astronomical units of the Sun and go out to 4.1 astronomical units. Do you know what an astronomical unit is? It's the distance simply from the Earth to the Sun, about 93 million miles. The comet's orbit is inclined at only 12 degrees to that of the Earth's. This low inclination and the shortness of the orbital period ensure that there is frequent interaction between the Earth and the material of the Taurid stream, with the potential for occasional very close encounters with Encke's comet. And this is from Technology Review, Peter Tyson Comet Busters. I've just found this may be apropos with regards to the encounter of clusters of objects. Recent studies have shown that a host of fair-sized pieces could have more devastating global consequences than a single winter-causing object, which would be in the kilometer range and above, by igniting many separate conflagrations that merge into a global firestorm. And we've seen that's exactly what happened with the firebombings of Dresden and Tokyo, is that the smaller fires merged into one great firestorm that seemed to have synergistically more energy than all of the combined smaller fires put together. And what this particular article in Technology Review was talking about was that this may be also a function of a clustered bombardment. So in other words, if you had multiple objects coming in that were on the scale of a Tunguska event, the consequences could be more devastating. In other words, you take the same mass and put it into a single object, bringing it in. But now bring that same mass, disperse it, disaggregate it, bring it in as a bunch of separate pieces, and it would actually have more devastating consequences over a greater geographic range than the single object. You might think of it, the way I think of it is the difference between like a single bullet and a shotgun blast. Any questions? Comments? Just an artist rendering that I thought was sort of expressed the idea that we're talking about here. Yeah.
I just recognize all of the cometary streams, the major big ones, are all oriented to signs that have planetary nebula with them. And there's a couple very specific nebula that correspond with the bowling alley, the Dansgaard-Oeschger, the younger Dryas, and they represent that scale of magnitude that we're talking about, that we're trying to find. So I wonder.
I didn't hear the first part of your question. Maybe if you could, somebody give him the megaphone. Do we have a microphone here that you can use?
Check.
Ah, there, that's much better.
So the scale that we're looking for is above solar and of the impact energies, the energy input that is indicated by the warming trends.
Okay.
Several of those trends, the Dansgaard-Oeschger cycles, correlate with the Cat's Eye Nebula and the evolution of that. The Helix Nebula is timed and oriented with the younger Dryas.
Okay.
And all of those major cometary streams also orient to zodiacal or astrological signs that have nebula within them.
Interesting. Now, I was not aware of that.
And that would bridge the gap between the solar flux that we recognize and these other longer duration, high amplitude temperature spikes. And you basically have a cosmic ray gun. The Helix Nebula itself is polar oriented to our solar system.
Yeah, maybe you could give me some resources that I could look at.
Sure.
Excellent. Thank you.
Hey, 2 questions.
Okay.
So I just wanted to make sure that I was following. So you said that the Taurid meteor, not the Taurid meteor stream, the surrounding meteors that kind of are
The Kuiper disk?
Kuiper disk.
Or Kuiper
exactly.
belt, yeah.
So you said that they're essentially regularly arranged now, and there's some kind of energy injected that can pull it into like coming towards the Earth. Is that?
Yes. I mean, something does. I'm just, the question is, what exactly does that? What causes the migration of comets from that reservoir into the inner solar system?
Okay. So
That's the question.
Yeah, my question is, do you have a hypothesis of what that energy?
Well, there is, I think I've got it coming up here. There's an interesting idea that was proposed maybe a decade or 2 ago that I think we've got coming up. So we'll address that.
Perfect. And then second question, it was a lot of slides ago, but you had a lot of moon impact craters. I'm assuming they were impact craters.
Yeah.
But the diameter of the craters, they seem to all be about the same depth,
Right.
regardless of the diameter of the craters. Do you know why that is?
Oh, well, that kind of gets us far afield into the structure of the moon. But yes, that's one of the kind of anomalous things about the moon is that there seems to be a maximum depth crater depth to diameter ratio that's extremely shallow. In fact, some of the larger craters on the moon are so shallow that if you were at the center of the crater, the mountains that formed the rim of the craters would be below the horizon. Well, what it tells us is the moon is an extremely rigid object, which raises a whole bunch of questions which are very interesting about the structure and architecture of the moon, the inner composition, and so on, which are kind of beyond what we're going to talk about today. But at some point when I'm a little more confident, because some of the thoughts and ideas about it are kind of on the outrageous end of the spectrum. So I'm not really want to go there. I'm not really too prepared, but we could possibly, we'll see how much time we have here today. We could possibly get into a few things relative to your question.
Thank you.
Sure.
Yeah, I just had a question for clarification regarding the Younger Dryas impact hypothesis.
Yeah, okay.
Is it that mainstream archaeology is denying that there was an apocalypse? Or is it this that we haven't found evidence of comet impact to verify it, so to speak?
I'm not really up exactly where I think you've probably got younger archaeologists now that are certainly willing to look at it. I mean, the evidence for the disappearance of the Clovis culture is quite robust at this point. Perhaps the Solutrean culture in Europe may have been affected. I don't know where they stand at this point. Certainly, I think, though, that they need to factor this into their thinking because, in my mind, it's pretty clear something happened. And we're also seeing evidence, more and more evidence. Like, I want to refer you to Stephen Collins' work over there on, what was the name of your paper, Stephen? Yeah, it's an excellent paper.
Okay.
In fact, I've recommended it numerous times. So, and I can give you a link, or I bet you Stephen can give you a link. I imagine it's downloadable, PDF. Yeah.
Yeah.
So I would highly recommend that paper.
Yeah, because I see that the human record shows us there were 7 comets that triggered the Younger Dryas.
There was what?
7 comets.
Oh,
That's why we have 7 snake headdress all around the world.
Okay.
Because there were 7 snakes that fell to Earth. The Mahabharata says 7 torches fell to Earth. In fact, the 7th one supposedly hit Northwest USA, which is why I'm so interested. That's what triggered the Younger Dryas. It was so big it made it look like dawn was coming from the west. And that's the morning star. That's Lucifer himself. Was a comet,
that's
the
an
7th
interesting
comet of the
idea.
apocalypse.
Yeah, I mean, I'm certainly somewhat aware of the fact that, a lot of the ancient traditions and so on are going to be very useful in deciphering these events, and that what you just mentioned could be that. I'm leaning towards the Younger Dryas event being multi-impact. I think that, I think some of the critics have kind of created a straw man by assuming that it was just a single object, large object, which then should leave a very obvious crater. But as we know from Tunguska, we can even have larger than Tunguska that is not going to leave that obvious crater. And if you had impacts into the ocean or into the ice sheet itself, then obviously you're not going to have the same type of a crater. Now, we can get into some of this if we have time today. I've kind of played with the scenario of what would happen with an impact into an ice sheet. And I can show you some stuff when we get into part 2 here of, I think that drumlin swarms may be a clue, geomorphic clue to impact sites in the ice sheet. But
the other part of the record was that it appears that the book of Revelation is actually a story of what happened, it's not what's going to happen. It tells you what each of the 7 comets did.
okay,
And so it coincides with all of it.
Okay.
And I'm wondering how much the human record could weigh in on a scientific discussion of the Younger Dryas impact hypothesis.
yeah. Well, I've read the book of Revelation many times, and of course, so much of it in there seems perfectly metaphorical for cosmic impact type events.
Thank you.
Sure. Thank you.
Hey, how you doing? So, given the prevalence of asteroids and impacts on the moving bodies, how much do you think that we have been able to observe versus what is out there? And then how, as far as like the Comet Research Group is concerned and tracking these bodies, how fast and how much would you feel safe as far as our ability to observe? And if we got to a certain number that we tracked, would we get a fair idea of what's out there?
Yeah, I think
My understanding that there's a very small percentage that we know about, and they seem to come out of the middle of nowhere. And at what point would you feel safe and that we have an accurate consensus of the bodies out there and the amount that could interact with us?
Well, I'm not at that point yet. I'll put it that way. That I think the larger objects, yeah, I think we've got a pretty good handle on the larger, kilometer and above objects. But not all of them, of course. We're also discovering that the possibility of dark cometary nuclei, which may change the statistical numbers somewhat. It's the smaller stuff. I mean, I think, it's the sub-kilometer objects that really of more concern to me. Not so much the planetary killers that are going to cause like a global mass extinction along the lines of the Permian Triassic or the Cretaceous. I still call it the Cretaceous Tertiary, but it's now the Cretaceous Paleogene. But the Cretaceous Tertiary event, we're looking at a 6-mile roughly asteroid producing a 130-mile crater, I don't think that that's the danger. I think the danger really is going to be smaller stuff, and like what Peter Tyson said in that quote from Technology Review, if we had a cluster, let's say if you had a couple of dozen Tunguska-sized objects or even several hundred. I mean, if we're looking at several hundred, now we're talking about an event on the scale of like an all-out thermonuclear war, minus the radiation, of course, but...
Or being able to track the activation events of a larger object, being able to break into a smaller object.
Yeah, I mean, we're identifying, I think that
Smaller object.
we're probably like what we know of, and again, the qualification was the question of dark cometary nuclei. Are there more of those than we've identified so far that have basically very low albedo? We don't really see them, but they're out there. They're dark objects that could come slamming into the Earth unannounced.
And as they get closer, then they may become activated, and then we see them
Perhaps, yes.
seemingly coming out of the middle of nowhere.
But hopefully we discover them before they're, on an Earth impact trajectory. But again, it's like the thing about Tunguska was that nobody saw it coming. And we'll look at some of the statistics of recent encounters here. We get a little further into it. But yeah, so my thought would be what we're more concerned about now is not the big planetary killer mass extinction events, but what I would call the city busters, I guess. If you had, a few dozen objects like this, that's why I cited this example of the 1913 meteoric train. If there were dozens of objects in there between 100 and 200 feet, now we're looking at dozens of objects that would be in the scale of the Tunguska event. And, and again, you saw it passed right over populated areas of the Northeast. If something like that were to happen again, that could be, again, it could lead to millions of casualties. It would not lead to a planetary extinction event, but it could still be very disruptive on a planetary scale. An event of that magnitude could disrupt the whole economy of the planet for years. That, to me, is really the more concerning possibility. Don't rule out, I guess, that, we discover some dark comet nucleus, but that's, statistically, I think it's far more improbable than, something along the lines of Chelyabinsk up to Tunguska, maybe a little bit bigger, but if we had a multiple event particularly, but even a Tunguska-sized event coming in now, let's say over the eastern seaboard or over a populated region of Europe, I mean, if that detonated over a major metropolitan area, you'd have several million casualties and probably tens of millions of injuries. That would be pretty significant event.
And then the solar forcing possibilities.
And then what?
And then if it just gets too close to the sun and the solar flare and coronal mass ejection as well.
If that's not just a coincidence. But I've got to do more study into that. I'm very intrigued by that possibility. I don't know enough yet to have any definitive opinions on it.
One final. Are you familiar with the electric universe theory?
Somewhat, and it may fit in with the ideas of plasma technology.
And
I'm not going to claim to be an expert on, because up to this point, so far, I've found that the idea of of impacts of comets and asteroids and possibly, the sun, which could then take us into the realm of plasma, of course. That's what Robert was saying. Have seemed to me to be adequately explaining the phenomena that we've seen. I could be wrong on that, but that's my impression at this point. But it's probably worth looking into. Right. I haven't looked into it enough to have. There's a lot to learn out there, and I only have one brain. I'm working on cloning myself so I can have at least one more brain. But I'm a little ways away from that yet.
So, thank you for your time.
Yeah.
Will you have a chance to discuss the Peshtigo fires?
Well, we could, I guess. Yeah, that's a kind of a whole thing. That's a fascinating, yeah.
Well, it's such a great example of a comet interacting with.
Yes.
Yeah.
Yes. Well, we'll see how much time we have.
Okay.
All right, so let's go on for a little bit more, then we'll take a break. I call this Ancient Legacy because this is some of the stuff that I've kind of come across that looks to me like it could be references to cosmic impact phenomena. William Whiston, who wrote in his book A New Theory of the Earth, from its original to the consummation of all things, wherein the creation of the world in 6 days, the universal deluge, and the general conflagration is laid down in the Holy Scriptures, are shown to be perfectly agreeable to reason and philosophy. How about that for the title of a book? And this is the quote from it that I always found really intriguing. We know no other natural causes that can produce any great and general changes in our sublunary world, but such bodies as can approach to the earth, or in other words, but comets. And we may observe a new possible cause of fast changes in the planetary world by the access and approach of these vast, hitherto little-known bodies to any of the planets. So he said that in 1696, which I find interesting because, he was, in a sense, he was one of the early catastrophists, as were a lot of the scientists, and particularly geologists in the early days, 1600s right through the 1800s, where most of them actually were catastrophists who believed that catastrophe was an integral part of the history of this planet. And they drew their inspiration for that idea from a number of sources, some of them from observations out in the field, some of them like Whiston with his probably observations of comets, others from scripture and sacred writings and traditions and legacies that have come down to us. So Edmund Halley, who used Newton's laws of gravitation to compute the orbit of the comet that bears his name and was thereby able to predict its return, also speculated that encounters with comets played a major role in Earth history. Like Whiston, he assumed Noah's flood to be historically authentic and proposed a comet as being the instrument of causation. In a paper presented before the Royal Society in 1694, he describes his conception of the effects of the shock of a cometary impact on the Earth. Quote, I have proposed the casual shock of a comet or other transient body. The great agitation such a shock must necessarily occasion in the sea sufficient to answer for all those strange appearances of heaping vast quantities of earth and high cliffs upon beds of shells which once were the bottom of the sea, and raising up mountains where none were before, mixing the elements into such a heap as the poets describe the old chaos. That some such thing has happened may be guessed, for the earth seems as if it were new, made out of the ruins of an old world, wherein appear such animal bodies as were before the deluge. Now, sometimes in my travels, looking over the landscapes of this earth, I come away with that very same impression, that the earth, it seems, as it were made new out of the ruins of an old world, of the and I'm going to show you in part 2 of this examples of that, what I believe are the effects of these gigantic cosmically induced catastrophes and the imprints that they have left in the landscape, and how we can learn to identify those, see them, that they can range from the inconceivably spectacular, like we see in some of the western states, particularly the Northwest, but also pretty much everywhere about us, once you know how to recognize even the more subtle effects of these hyper-scale events, particularly involve the extreme movement of water over the landscapes, which leads me to, the insight or the conclusion that, so many of the flood myths that have come down to us from all parts of the globe are based upon real events. And that these events are not just, in fact, I was recently, somebody was criticizing me online. It was an archaeologist, as a matter of fact, saying that, well, these stories are just exaggerated versions of regional events. And my thought, in fact, I think I may even do a response to that to say, well, excuse me, but a peak discharge of 500 million cubic feet per second is not a regional event, okay? And I'm going to show you what the passage of 500 million cubic feet per second over the landscape looks like shortly. Fred Whipple. Fred Whipple was a Harvard professor, director of the Smithsonian Astrophysical Observatory, a presidential medalist, and his name is synonymous with comets. He was one of the few great innovative thinkers in 20th century planetary science, yet through it all he remained just Fred to all who knew him. Whether you were a young student or a distinguished internationally recognized scientist, this gentleman treated everyone with the same kindness and respect. The entire planetary science community has benefited immeasurably from his wide-ranging insights. We've lost a creative scientist. We've lost a creative scientist and a kind mentor, but he remains a superb role model for us all. This is from the obituary by Donald Yeomans, appeared in the journal Nature. I had become aware of Whipple's work, I guess, around the late 70s, and the photographic evidence that I showed of the Taurid meteor shower was based, the evidence in that graphic I showed you, it was based upon his photographic studies of the Taurid meteor shower. And here is some of I missed Chandra's presentation. How many of you saw it? Good, okay, so these are some of the books I would recommend. If you want to get more deeper insight into this, there's Coulee and Napier's work, The Cosmic Serpent. That was one of the early books I read. I remember I've got a hard copy version of it that came out that I bought probably within a year of its first publication, and 1982, although they've done a lot of work since then. And they've done one called The Cosmic Winter that's worth reading, and I think you can download the entire book online. I believe I've found it in PDF form. And then Chandra's book, The Cosmic Dragons. Now what's interesting about this, both of these titles invoke images, on the one hand a serpent, on the other of a dragon. This is a very typical way of representing ancient cosmic phenomena like meteors, fireballs, comets, and so on. Yeah, there's The Cosmic Winter, and then also Evolution from Space, a theory of cosmic creationism, which leads us in some very interesting ideas, and the idea that perhaps life on Earth was seeded from the cosmos. And we do know that the precursors to life, to the biogenic precursors, are found in comets, even in asteroids. So these are just, if you want to dive deeper into this on your own, and then Stephen's work, like I recommended, his paper on Tel el-Hammam is really a good read. And go to Google Scholar, you'll find it right there. You can download it, print it out. Which brings us to the deluge, or the great meltdown. So what we're going to do is we're going to segue from the sky to the earth. And we're going to look at some of the catastrophic events on the earth, that I think may be related to activity in the sky, okay? So I called this part of my program the deluge, the great meltdown. Now, obviously, I think one of the things Robert and I are in total agreement on is that there was a great catastrophe around the time of the Younger Dryas. Part of that catastrophe included gigantic floods, really gigantic floods. And those of you, let me see, anybody out there who's been on any of the tours? Okay, so were you on the Cumberland East tour, or were you on the Scablands tour? And Montana? Okay, so you have a pretty good idea of what we're talking about. So you know we've covered hundreds of miles from western Montana across eastern Washington, across northern Idaho, and we're seeing the effects of a flood that affected all three of those states, plus Oregon, plus Alberta, plus British Columbia. So this is really just more than a regional flood, in my opinion. When the archaeologists say, well, this was just an exaggeration, you know, the idea of the Great Flood, it was just an exaggeration of a local or a regional flood. And I remember encountering this decades ago. They're still stuck in that paradigm. They have not kept up with the evidence of paleohydrology, which is what we call this particular discipline, the study of ancient water flows. So I'm going to introduce you here to, I know some of you are going to be familiar with this, but we'll get into it just so you can get a kind of wrap your head around this and why I think that the current models, the current explanations for these floods don't really make sense. So the Ice Age Floods Institute, when my buddy and colleague Brad Young and I first visited that in 1998, the Ice Age Floods Institute had one headquarters that was in the little back office of the Chamber of Commerce in Moses Lake, Washington. And it was staffed by one very sweet little old lady who was the only one in there. And they had one chapter. Now I don't know what they've got, a dozen, 20, somewhere in there. The interest in this phenomena has grown exponentially since that year in 1998. In 98, that was actually the first year we were able to go and make what I think of as kind of a scientifically oriented reconnaissance and becoming familiar with the landscapes and so on. My discovery of all of this went back, I would place it in the year 1979 to 1980. I actually crossed, traveling as a very young guy, just out of high school. In 1970, I crossed the Scablands and traveled up through the Columbia Gorge and saw the evidence of these gigantic floods, but had absolutely no clue what I was seeing. But I had an impression that stuck with me, and I've used the analogy of, you know, from Gulliver's Travels when he was in Lilliput. The Lilliputians were the little people there. And I remember coming away from that trip with this almost sense that I was like a Lilliputian in this landscape of giants. And in a sense, that's what it was, because the phenomena, and I'm going to show you some scale invariant phenomena here, that you can see water does very similar work regardless of the scale. And that's why, you know, if you were to take a hydrology course in a university, you would probably have in one of the labs, you would have a stream table, it's called. It's usually diatomaceous earth, and you've got sources of water where you can control number of variables. You can control the volume of the water, you can control the velocity out of a spigot, and you can control the tilt of the stream table, which recapitulates the gradient of the landscape. And so you can create all the landscapes that water create, but in miniature. Now, I have a stream near where I live that I like to go to and walk along, particularly after heavy rainfall, to observe the geomorphic work that's been done. And I'm going to show a few examples here, but you can see once you start paying attention, you can see just walking along a normal stream or river, along a sandbar or a gravel bar, and then what you're going to see on landscapes where it's the result of mega floods. And one of the things I've learned now about traveling over these landscapes is that the scale of the phenomena is so huge, is so grand, that you oftentimes don't even really understand what you're looking at. And I'm always surprised at the number of locals who just don't even have a clue of what the landscapes that they're living in. It's just, it's just to me that, I mean, I guess I just have never had that psychological orientation where I have not had any curiosity about the things around me. Because I mean, even growing up in rural Minnesota, I was always interested in, it was like, why is that? Okay, we got this flat field, but right out in the middle of that flat field, there's a hill. Why is that hill there? Or the lakes. Like I lived on a lake, and it was part of a chain of lakes. And I then learned, I guess at 7 or 8 years old, that there had been an ice age. And then as I got older and I learned more, I learned that right where I lived and grew up was sort of at the edge of what's called the superior lobe of the Laurentide ice sheet. And so throughout the course of the ice age, that margin of the ice sheet wasn't stable. It moved, it advanced, it retreated, advanced, it retreated. So I was kind of living right in that zone of advance and retreat. And so it pretty much 100% sculpted and created the landscapes I grew up in. And I can even remember being just even a small kid, and certainly by the time I got 10, 11, and 12, playing out there, there was a big hill next to our house, and I would go sit up on that hill, and I could just look out. I could see the lake, and I could see kind of the contours of the land. And I couldn't put words into it at the time, but I always got this impression that there was, there's a story there, that it was almost like I got this sense that the landscape was trying to speak to me, but I couldn't understand it. I just was sort of in a way entranced by just the lay of the hills and the way particularly the sun goes. A lot of times this hill was to the east of where I lived in the house, so I would oftentimes go on the hill. Sun would be going down in the west, and then the low sun angle, the shadows of the sun angle would really bring out the contours of the landscapes. And I just got that impression at a very early age that that there was something unique. And I guess that kind of carried over into my adult years. And this, I read a couple of books about Atlantis in the late 70s. One of them was called The Secret of Atlantis by a German physicist named Otto Mook. And he proposed that Atlantis was sunk because of a bolide impact into the Atlantic Ocean. And this was an interesting time because in 1980 is when 3 separate independent authors or teams came out with similar scenarios for the extinction of the dinosaurs at the Cretaceous Tertiary boundary, 65, but now it's been refined to 66 million years ago, that it was an extraterrestrial cause. And there's 3 of them that came out in 1980. And I always kind of consider that sort of a turning point year in our acceptance of catastrophism, that catastrophes have happened in Earth history. Now, the evolution from there is that, 1980, it was proposed, but there was a lot of resistance to it because, gradualism or uniformitarianism was deeply entrenched as a paradigm into the thinking about Earth history. But that changed, that inflection point was the year 1980. And it was then that we go, okay, well, it looks like the dinosaurs got killed by an asteroid impact. Well, that means that the dinosaur extinction was catastrophic. It wasn't gradual over millions of years, it was catastrophic. And so it took another decade, I think, before most of the scientific community accepted that. For a long time, it was a controversy between 2 catastrophic scenarios, one impact from outer space, the other volcanism. I now think it was both, because we do know that the extrusion of the Deccan Traps took place pretty much centered right around the KT boundary, and it was extremely catastrophic. But interestingly, the outpouring of the Deccan traps was at the antipode of the impact site. So it has been proposed, and perhaps it makes sense, that there was the impact. I mean, you think of a 6-mile dense space rock slamming into the Earth at 20 miles per second. It's going to cause a seismic ripple that travels around the entire globe. And then it's going to meet at the opposite side. So the idea that perhaps the volcanism itself was a consequence of the impact. I haven't seen the latest studies on that, but the timing of it, the duration of those basalt floods that formed the Deccan traps has shrunk considerably as dating has improved. So it's very possible that there's a connection. The other fact that I think is very plausible is that the big impact that left the crater in the Yucatan wasn't the only one clustered around that boundary. I think there could have been, and probably was, multiple impacts, that we probably were during a period where the Earth was susceptible to some, it's been proposed a comet storm. The object that struck the Yucatan, I believe the latest evidence suggests it was probably an asteroid, but also studies are also blurring the division between asteroids and comets, that there's now kind of a middle ground where things that we believed were asteroids might actually be devolatilized cometary nuclei. In any case, 1980 was kind of a turning point, and it took about 10 years, and most of the doubters were saying, well and good, but until you can show us a crater, we're not buying into this catastrophic impact scenario. Well, eventually they found the crater, and it straddles the Yucatan Peninsula, Gulf of Mexico, and it's about 130 miles wide at least. It's buried under nearly half a kilometer of limestone rock, and it dates precisely to the KT boundary. And we've been able to find the tektites, and there's actually evidence now going up into Louisiana and Texas of a huge tsunami that made landfall that resulted from that impact. It's pretty much accepted by the scientific community. Now, that was associated with one of the great impacts in the history of life on Earth. I mean, one of the great mass extinction episodes in the history of life on Earth. One of the so-called Great Five. There was 4 others. Probably the most severe being the Permian-Triassic event. Now, it's known that there was a volcanic outpouring similar to the Deccan traps that took place during the PT boundary. Was there an impact? Well, it's not known for sure, but there is some evidence that there could have been a great impact or even several impacts. Likewise, at the late Eocene, now another one of the great extinction episodes occurred in the Ordovician. There was a late Cambrian. There was a mid-Jurassic. So there's been a bunch of them through Earth history. The Great Five, though, you're talking about at least 3/4 of all species of life on Earth erased. But there have been multiple smaller extinction episodes, almost too many to count. Now, these smaller episodes, like, for example, Tunguska, no mass extinction at all. The Younger Dryas, there was mass extinctions of half of the megafaunal species of Earth, disappeared. Now, what the prevailing explanation has been for that for many decades, and it's so, to me, so incomplete and so unable to explain what happened, but nonetheless, it was basically boiled down to human hunting, overhunting. And I don't know how you eliminate half the species of great megafauna on Earth. We joked on Cosmographia with Russ and Kyle Allen, talking about, Birkenstock-clad hunters in their loincloths with spears chasing the woolly mammoths down. But I've read, trying to come up with a census of, okay, at the boundary of the Younger Dryas, just how many people were there in the world? Okay, so the estimates that I've seen have ranged between 5 and 10 million people globally. That's not very many. How many mammoths were there? Well, the estimates I've seen for the global census of mammoths is about 12 million. Okay, so what that means is that there was more mammoths than there were people. Now, if you take the total number of people and you assume that the hunters were mostly grown men in their prime, what is that, 25% of the people? I don't think it's, you don't have 5-year-olds and 6-year-olds out there hunting the mammoths. You don't have 80-year-old men or women. You don't have pregnant women out there, presumably. And so what does that leave? I mean, so you're talking about, okay, so if there's, let's say 10 million. Well, let's say there's 2.5 million viable hunters globally, but they're responsible for killing off 12 million woolly mammoths. How is that even possible? I mean, how do you, I mean, that you presume, now you're talking about every single mammoth, every last one has to be killed. Now, of course, Robert mentioned the word yesterday, taphonomy. Now, taphonomy, I'll define that. Taphonomy is the process that occurs between the death of an animal and its introduction into the fossil record. And there's a number of different processes by which that can happen. But typically, if animals die in nature, like now if you look at an animal dying in nature, their carcass does not become part of the fossil record. No, their carcass is consumed by scavengers and bacteria and erosion. I mean, even during the 80s, when there was this mass, 3 or 4 million elephants died because of the extreme droughts. And there would be multiple elephant skeletons gathered around watering holes that had dried up. So paleontologists went out there and studied that, and what they learned was that even an elephant skeleton just laying there on the ground was pretty much gone, reconsumed within about 5 or 6 years. So the point is that when you talk about preservation of animals, you have to remove them from those their carcasses from the circumstances under which they would be recycled into by nature through multiple different ways. So how do you do that? Well, first of all, the first thing is you have to bury them so that they're away from oxygen, they're away from scavengers, they're away from the microscopic entities that would be consuming their remains, and that's how they end up in the fossil record. Now, out of Siberia, going back hundreds of years, there have been thousands and thousands and thousands of mammoth remains found. In fact, there was a whole industry of mammoth tusks during the 17 and 1800s where they would come in with whole shiploads of them, and I've got some slides. Maybe we can get into those somewhat. But here's my point. The mass extinction of the megafauna, and of course we're just talking about one species. There were over 100 species of megafaunal animals that went extinct somewhere. Now Robert says, and this could be right, I think there was a major pulse of extinction at the lower Younger Dryas boundary and a major pulse of extinction at the upper. So let's say in round numbers 12,900 and 11,600, right? And then after that, you don't find the giant ground sloths, look, where we are right now, there was at least one species of mammoth and mastodons roaming through the forests of North Carolina, which by the way, at that time, were similar to the forests you now find in Canada, with spruce trees, larch trees, alder trees, what you would call a boreal forest, a northern forest. It was not the same trees as you find in North Carolina now. There were camels, huge camels in America who, with their humps 7-8 feet high. You had the cave bears, Ursus spalius. You had Castoroides, the giant bear-sized beavers. You had the American Pleistocene lion that was almost as big as a horse. The list goes on and on. I mean, and of course they're all gone. So my question is to these paleontologists is, well, did spear-throwing hunters kill all of those animals? And the more you think about it, it just doesn't make sense. But so entrenched were the gradualistic models that they realized, I think on some level, well, if we admit that it wasn't hunters, then what was it? Well, okay, it was climate change. Okay, so now it's like the two contending views are Paleo-Indian hunters or climate change. But then when they talk about climate change, oh, well, climate change, maybe you're moving in the right direction. Then you read what they're talking about. Well, it was probably global warming that did it. You know, in other words, they're invoking a scenario that is not unlike what's going on right now and what has happened since the end of the Little Ice Age. In other words, they're anthropomorphizing it. And they're saying, well, climate change, they're using it as an analog for what's going on now. In other words, it's not some catastrophic event in the sense of a solar outburst or an asteroid impact or gigantic volcanic eruptions. It's something that's similar to what's going on now. And because of that, it's fueled this scenario of we're in the middle of a sixth great mass extinction, right? Comparable to the Great Five, which when you look at it and particularly use the KT catastrophe as a model, is just ridiculous. It's totally ridiculous. But in any case, that's where it's kind of left. Now, I think that slowly we're shifting to the idea that, yeah, there was a catastrophe coming out of the Ice Age, and the mass extinction of the megafauna was part of that catastrophe. And it's getting harder and harder to evade that conclusion, even though they're trying their damnedest. And I think that the attempts to evade that conclusion are mostly driven by essentially by political agendas. But anyways, Ice Age Floods Institute has grown exponentially since the 90s. I was pointing out that my interest in that area really began, I think, you know, I would say I was gradually coming to understand catastrophism throughout the 70s, and I met a gentleman who was writing a book in 1978, and one of his primary sources was Charles Hapgood. How many of you are familiar with the work of Charles? Oh, quite a few of you. That's good, yeah. Now, he wrote a book called Path of the Pole, which he later kind of repudiated his own idea, but he didn't repudiate the idea that there had been a catastrophe. He just, you know, kind of left it open as to what was the explanation for the catastrophe, if it wasn't a pole shift, okay? But what I discovered that book, this friend of mine who was writing the book told me about it. He was using it as a reference, and it was not available. It was out of print at the time. I thought, man, I sure would like to get that book. And of course, he would not relinquish it. He wouldn't loan it to me because, for one thing, he was using it. You couldn't go online and find stuff back then. And I just happened to go into a library book sale one day in this tent in a parking lot, and there it was, a hardcover version of Path of the Pole. So for like $1 or $2. So forked over my money, got the book, went home, read the book, and it has an extensive bibliography. So I set out a goal. I was going to try to track down every resource that he referenced in that book, like over 300 references. So in the county that I live, DeKalb County, there's a science center. It's called Fernbank Science Center. It's kind of affiliated with the school system, but they have a public science library there. They have a great science collection of tektites and fossils and all kinds of things, and shows and programs that they do. They have an observatory, a telescope, all of that, but they also have a science library. So I went in there and I started researching. One of the things I just came upon was the Carolina Bays. I found a book, a reference. In fact, when I read these two books on Atlantis, one of them was called, I don't remember the full name of it. It was Cedric Leonard was the author. And he talked about the Carolina Bays. No. It was Edward. It was Otto Mook, the other guy I told you about. He mentioned the Carolina Bays, and then Leonard mentioned the Channel Scablands floods as evidence that there had been these giant floods. And when I read that, I remembered that, yeah, I crossed that landscape, in 1970. And had no idea what it was, but I just got fascinated by it. So there was two things, the mention of the Carolina Bays and the mention of the Scablands flood. So I got obsessed for about the next year or two tracked down every single thing I could find on the Carolina Bays, every single thing I could find from the references in Hapgood's work, and everything I could find on the channel Scablands. So I just spent like the next probably couple of years just immersed in that, researching and reading and everything. I didn't actually get out there to the Scablands until '98, but by that time I had read every paper that Harlan Bretz had written and pretty much everything else that had been written on the subject by other researchers subsequent to Bretz. So I kind of knew what I was looking for, and I've lost count, 25 or 30 trips over these landscapes since then, exploring every nook and cranny to try to understand what actually happened, and have become completely convinced that the prevailing dogma that there was this gigantic lake in western Montana held in by an ice dam just doesn't make sense, just like the anthropogenic explanation for the extinction of the megafauna doesn't make sense. And it's interesting, as I learned more about taphonomy and the circumstances under which megafaunal remains were found, was they were more often than not found in deposits that would have been the consequence of really big floods. Now that could be gravel pits, it could be peat bogs, it could be permafrost. Some of the permafrost deposits in Alaska and Siberia are amazing things. They're just huge conglomerations, like many times thicker than this room is tall. And in there's just countless remains of megafauna. And when you become aware of that, you realize that, now wait a second, this had nothing to do with human hunting at all. But that kind of evidence just seems to be ignored altogether by the promoters of this human hunter, which was really going out of fashion until recently. But see, with now the the extinction, what is the environmental group? The Extinction Rebellion, who they're one of the groups that go out and lay down on the highways and stuff to block traffic. And of course, they're the ones proclaiming we're in the midst of a sixth great mass extinction. And so there's a whole political agenda now that our activity is causing the sixth great mass extinction. And so one of the things they invoke in support of that claim is the extinction of the megafauna. Well, you see what we did already. You let humans go and see what they're going to do. They're going to decimate the whole ecosystem, and they're going to kill off, all of these species of animals. Here's a little perspective. The number of megafauna species that went extinct during that younger Dryas period, around that window, that number of species is roughly equivalent to the number of species of megafauna on Earth today. So if you wanted to actually simulate an equivalent extinction event today, you'd have to kill off pretty much every single animal on Earth over 100 pounds in body weight, and then you would have created an extinction episode of the equivalent severity to the younger Dryas episode. I just don't buy the idea that human hunters were responsible for that. In fact, it's just the opposite. The evidence is showing that humans suffered a near extinction event as well during that period of time. And I don't know, we won't have time to talk about that today, but I am going to be covering a lot of this in detail with graphics and all kinds of cool stuff on my Squaring the Circle podcast. So the result of all this is we went out there in '98, went to the Flood Institute. One little old lady sitting there, I remember she was very sweet and very kind and thought it was really great that somebody showed up and who actually was interested in these floods, and how remarkably it's grown and how exponentially it's grown since '98. This is their tagline: it may be the greatest story yet untold. And I would modify that a little bit to say it is the greatest story yet untold. And let's get into it. So this is a satellite view taken back, I think, actually in the 70s. It's a NASA, and what you can see here, if you're looking, is, let me see, do you see my cursor? Oh, good. Okay. So here we have what's called a channeled Scabland tract, and here we have another one over here. And what the situation is here is this is the Columbia Basalt Plateau, which was one of the great outpourings of flood basalts that occurred. It started around between 16 and 17 million years ago. It lasted till about 6 million years ago. And you had this repeated succession of these great basalt floods, liquid rock, melted rock, just gushing out over the earth, created this plateau, which in some places is a couple of miles thick of crystallized basalt rock. Once the floods subsided, then you had the formation of soil and things on top, and you had one of the soil deposits, the thickest is called loess, L-O-E-S-S. And when you're looking at this image right here, you've got the tract itself, which is darker, because what you're seeing is the basalt. The dark, that's the bedrock that's been exposed. And then the lighter areas, which are also farms and agriculture, is the loess topsoil. In some cases, it's 200 and 300 feet thick, laying on top of the basalt bedrock. The floods came from the north. This is my opinion, because I think the evidence is consistent with that. And the main scientist who first studied this, starting back in the 1920s and wrote a succession of papers, was J. Harlan Bretz. And his first impression was that these floods, these two tracts here, the one on the left to the west, right here, is called the this is the Telford Scabland tract, and this one is the Cheney-Palouse Scabland tract. So we go over all of this when I do the tours. We have briefings where we get together and I show this and I explain it all so people can learn the terminology, and we sort of go over the maps of where we're going to be visiting so it's not just a sightseeing tour. That's the point. It's about learning the science of paleohydrology. So you got these two great Scabland tracts here, and then over here to the west, you have this feature coming down here, which is called Upper Grand Coulee, and then here you have Lower Grand Coulee, and this was a great channel. It varies from 1 to 5 miles wide, 800 to 900 feet deep, and it was cut by these gigantic floods. And the estimate is that the peak discharges were around 350 million cubic feet per second. Now, how big of a flow is that? Well, to give you some idea, if we could take the entire planet of Earth, every continent, North, South America, Eurasia, Africa, Australia, every continent, and we were to take the flows of every single river on Earth. Think about North America. The biggest rivers are Mississippi, Missouri, Columbia. You've got the Mackenzie. You've got the Hudson River. You've got the Connecticut River. You've got the Rio Grande. We could take all of those rivers, and those are only the major ones. Go to South America. You've got Amazon, the Orinoco. You've got multiple rivers in South America. Go to Africa. Think about the Nile. Think about the Congo. Go to Eurasia, the huge rivers there, the Yellow River in China, the Po, the Rhine, the Rhone, the Thames River, all the rivers on Earth. Add them all together, it wouldn't even be 1/10 of the flow that created Grand Coulee. So obviously there's nothing like that in recent history, in recent natural history of the Earth. Then over here, you've got another. Now, the difference between a coulee and a channel is this. A coulee basically does not have flowing water in it, or the flowing water in it is so insignificant that it had nothing to do with the formation of the coulee itself, right? So it's distinguished from a channel. Like a river channel will have a significant river flowing in it. And if it's created through generally protracted slow erosion, what it does is it tries to create a V-shaped channel. Now when you look at coulees, you have sheer vertical walls, right? Because if you can picture this, now look at my hands up here. Imagine you've got flat ground, bedrock, let's say, and you have a fracture. It could be a fracture, it could be a fault line in the earth, right? Now, you've got water pouring over. Now, this is water that's moving at perhaps anywhere from 20 to 60 miles an hour, depending on the gradient of the land. Now, as that water is moving, what the water is wanting to do is to exploit any weakness, right, in the substrate that it can. So if there's a fracture or a fault line, the water will begin to penetrate that, and it'll exploit that. It will initially erode relatively slow, but again, if you've got overlying, let's say you've got, dozens of feet of water or even hundreds of feet of water on top, there's pressure at the bottom of that water column that's forcing the flowing water into the apertures, into the cracks, into the fault lines. So it moves into the fault lines, and now it's moving through that fault line or through that fracture under pressure. So what does it do? Well, it starts eroding the sidewalls. And then as the crack begins to enlarge, what happens is more and more water from the surface is now captured down into that channel. Does that make sense? Okay, so then as more water goes into it, it accelerates the erosion. Now let's say that water continues for a few days, a few weeks, a few months, whatever the case may be. At the end of that, whenever the source of the floodwaters ceases, you now have a vertical walled channel. We call that a coulee. So that's a coulee. Also, they can be called slot canyons if they're smaller. Same process. A slot canyon is just going to be a narrow canyon, but if you start pushing water through it under pressure, it'll widen it this way. It'll also deepen it, so it's widening it this way and it's deepening it. And what you end up with is a cross-sectional profile that's almost rectilinear, right? Rather than V-shaped, right? So this is really one of the indicators of major water flows, okay? So that's what we'll find in Grand Coulee. I'm going to show you some photographs here in a minute. Now, over here, you've got another coulee. It's called Moses Coulee. It comes down this way. You can see it doglegs to the west right here, and then comes down and it flows, it opens into the Columbia Valley right here. And then you're also going to notice that there's this kind of arcuate feature right here that's darker gray, right? That's pretty obvious, right? You see that? Okay, so that darker, what's happening there is south of that gray arc, you've got topsoil, and it's being farmed. But as soon as you get to that gray arc, what's happening is you're into a terrain that's composed mostly of terminal moraine. Now, what is terminal moraine? Okay, terminal moraine is the material that forms at the snout of a glacier. Now you picture a glacier is coming from whatever its source is, and here this glacier is called the Okanagan Lobe, after the river, the Okanagan River, which you can't quite see here, but it's the Okanagan River, and this is the Okanagan Lobe of the Cordilleran ice sheet. Okay, the Cordilleran ice sheet, I talked about some of that, I think, yesterday. I showed the Laurentide, I showed the Cordilleran. I said the Cordilleran is about the size of the modern day Greenland ice sheet, and I showed that the Laurentide ice sheet is approximately the size of that now covering the South Pole, the Antarctic ice sheet. Imagine you take the gigantic 5 million square miles of the South Polar ice sheet, you pick it up and you set it down over North America with its center roughly on Hudson Bay. So it now reaches from the Arctic Circle down to the northern United States. At the same time, we go when we get the Greenland ice sheet, we bring it over and we drop it over western North America, and now it reaches from Washington State up to Alaska. And we've got 6 million plus miles of glacial ice covering more than half of North America. So, like I mentioned yesterday, all of the northern cities from Boston, New York, Philadelphia, Detroit, Chicago, Twin Cities of Minneapolis, Seattle, they were all buried under thousands of feet of ice. And we're only talking thousands of years, not millions, thousands of years ago. So that's a pretty remarkable change. Okay, so what we have over here, whoops, is, let's see, I think there we go. Did that come back? Okay, so what we have, stop that behavior right now. Okay, what we have right here is the terminal mooring. Now, picture this. As the glaciers are growing, you've got a zone of accumulation and you've got a zone of ablation. So the ice, snow falls over the zone of accumulation, it piles up, the weight of that causes a slow movement, a flowing movement within the glacier. It's almost like living ice, but as that glacier is growing and moving over the landscape, it's gouging up the ground beneath it, right? So you can think of it in a simplified form as almost bulldozing, but it's a little more complex than that because material is actually entrained up into the ice mass itself, conveyed along almost as if it's on a conveyor belt. And then, of course, what happens is when it gets to the snout of the glacier, all of that stuff gets dumped. Then when the glacier melts, it recedes back, it leaves this very distinctive calling card which you can then use to determine how far the glacier advanced over the landscape. I think that's making sense. That's what we've got right here. So this was the Okanagan lobe, and you can see the terminal moraine forms this arcuate feature, and you can see that the channel, this scar in the landscape, which is a tremendously great, impressive scar. How many of you have been on a tour with me and we've been down Moses Coulee? Anybody here? Well, Pat, I know you have. Would you agree with me that it's one hell of an impressive feature? What did he say? It's one hell of a impressive. Yeah. Yeah, when you're standing on the edge of this thing looking into it, it's just phenomenally huge. And then when you realize, wait a second, are you telling me that this thing was full of water? The answer is yes. So anyways, you see here that Moses Coulee, as it's called, after Chief Moses, he was one of the, I forget what tribe he was, but anyways, you can see that the scar extends off the snout of this terminal moraine here, which to me always suggested that it was emanating directly from the ice sheet itself. Now the current theory is that Moses Coulee didn't come from north, it came from the east, and I'll show you, see what I'm talking about in a minute. Here is a color aerial photograph where you can very clearly see Telford Scabland on the west, Cheney Palouse over here on the east. You can also see they're kind of interconnected in a few places. If you look at this coulee up here, it's coming off of Telford, flowing down this way over to Cheney Palouse. This one here, which is the Crab Creek coulee, is extending off of the Cheney Palouse and flowing to the west. But what we see here is that you can see that the dark areas are very distinct preservations of where the water flew, where it flowed. So you can see that there are almost would have been like islands of this lush topsoil within the flows of water. Now the topsoil varies between 100 and 300 feet thick. So the first thing that happens is the water is flowing over this land and it quickly eats its way through the topsoil and gets to the bedrock. Okay, once it does that, now it's flowing over the bedrock and it does this, what I described earlier, channelization. The water's flowing over the surface, spread out, and then it begins to exploit the low areas or the cracks, the fractures, and so on. And then what will happen is once they get deep enough and big enough, they will capture all of that water from the surface. So now you just have bare bedrock, but you will have these channels with the water flowing in it because the channels have captured the flow. Is this making sense? Okay, good. Now, when we look at Cheney Palouse, you can see it basically starts right about here. Now, my impression is, the city of Spokane is right here. In fact, the area, the airport that you ever fly into Spokane is right in this area. And there's a series of lakes right in here called Medicine Lakes. But my impression is that this probably marks the terminus of what is called the Spokane lobe of the Cordilleran ice sheet. But the problem is the floods that came down through here remember I said 350 million cubic feet for Grand Coulee, 10 times the flow of all rivers on Earth. The flow that came down through this area was double that. So I don't think there's any really much moraine left because it was all flushed away in the process of these gigantic flows. But I think that this is probably originally when the floodwaters first came on, this area right in here was where the lobe, what's called some have called it the Spokane lobe, others have called it the Pend d'Oreille lobe. Others have called it the Purcell Trench lobe, but it's all the same idea. There's a tongue of ice that came down. You'll see it in one of the graphics coming up here, and you'll see the whole configuration of the landscape. This up here is this is actually the Spokane River here, flows into the Columbia River coming out of British Columbia right here. It arcs to the west. Right here where you see this change in width, that's where the so-called Grand Coulee Dam is. And we always will visit, there's an overlook there called Crown Point. We'll overlook where you can see the mile-wide channel. You can see the Grand Coulee Dam, which is over 400 feet high. And I like to point out that this was right at the edge of the Okanagan lobe. Right where that dam is, that was the edge of the Okanagan lobe where the ice was thousands of feet thick. And where the water that came through there was many, many times the volume of the modern Columbia River. The river down here at the bottom is the Snake River. And you can see the water flowing down that's carving out the Cheney Palouse hits the Snake River right here. And in fact, the flows, when they encountered the Snake River, reversed the flow of the Snake River almost 200 miles to the east. And there's a place there which we're hoping that in a future, our next one of our next tour, in fact, the next tour that we're going to do in September, there's a huge gravel pit right there where the flood waters, where the back flood in the Snake River terminated. And what's interesting about that is the second largest flood documented in North America is the so-called Bonville flood. The timing between the Bonville flood and the Missoula flood is interesting and rather controversial. I think they happened very close together in time. But anyways, the Bonville flood, how many of you ever heard of the Bonville salt flats, where high-performance racing cars are tested and everything? This was the bottom of this vast lake that covered nearly 100,000 square kilometers, almost 1,000 feet deep at the end of the last ice age. If you fly into Salt Lake City, or just in Salt Lake City, if you look to the east, to the Wasatch Mountains, you can see the shorelines of Lake Bonneville above the flats that Salt Lake City is built upon, almost 1,000 feet up on the side of the Wasatch Mountains. And this flood burst through a sedimentary dam. Actually, what I think happened is that there was an enormous amount of rainfall. This Lake Bonneville rose up to nearly 1,000 feet deep, and the lowest saddle, that Great Salt Lake Basin has no outlet to the ocean. That's why the Great Salt Lake, if it rains, it'll fill up a little bit, but then it'll quickly evaporate down to what it is now, which is just a few feet in depth, right? It's the remnant of this great late glacial lake called Lake Bonneville. It rose up to above this peak, where it's in a place called Red Rock Pass, and we're actually planning a tour to follow this flood, and it's an amazing route. And I think I've got some pictures here of it I'm going to show you in a minute. But think of this now. You've got this soft rocks, mostly sedimentary rock. It's about 300 feet thick. And it's sitting on top of a hard granite rock. And that granite is the sill. The water rises up, it spills over the top of this blockade there, and it quickly eats its way down through 300 feet of softer sedimentary rock. And then when it hits that hard granite sill, it stabilizes. And when you look up on the shorelines in the Wasatch Mountains, you can see the higher shoreline is when it rose up to overtop the dam. And then it took about a year to drain down, flowing at about 40 million cubic feet per second discharge out of there. When it hit that granite sill, it stabilized, and you can see that second shoreline on the mountainsides. So when we do the tour, we'll point all of that out so you can see that. And then what we do is we'll follow the route of that flood through the pass up onto the Snake River Plain, and we'll follow it to the west. And there's some amazing stuff along there. Now, this flood is not as huge as the Missoula floods that created this stuff that we're looking at here. But here's what I'm getting at. There's a place called Tammany Bar along the Snake River. And it's right at the limit of when the waters of Cheney Palouse hit the Snake, they reversed the flow of the Snake. And you had this huge surge, almost like a tidal surge, that moved backwards up the Snake River, up current, right? And it's supercharged with, look at here, all of the sediment. Picture, you can see all of the sediment that it's ripped up and is carried along in the water. That surge is moving upstream, right? Now it gets to this place called Tammany Bar, and when you go there, you can see that they've been mining the gravel there for decades, but you can see that on the bottom is this big gray bouldery stuff that was the Bonville flood that was coming down the Snake, down current, and sitting on top of it is this fine buff-colored silty stuff where you can actually see the layers in it. It's very impressive to see. That is the Missoula flood backwash that came up, and these two floods met right there. Now there, Brad Young is trying to get us access to the gravel pit, maybe even if there's a geologist in there who would actually allow us in and maybe even give us a guided tour through there and explain. But it's very clear. You can see the distinct two different kinds of sediment very clearly. And I think that it could be very significant to understand, because the first thing I noticed, the first year we went there, which was 1998, was that the line of demarcation between the Bonville flood deposits and the Missoula floods was very distinct, and there appeared to be no hiatus between them. It appeared as if the Missoula flood sediments were right on top of the Bonville flood sediments. Now, if that's the case, then there's an implication there. They're happening very, very close in time. So how do we explain that, right? In one case, we have a giant lake, the theory is, and it spilled over a sedimentary rock dam, and that's in Utah. On the other hand, we've got this giant lake up in western Montana that's being held in by glacial ice. So it's a glacially dammed lake. It breaks through that glacial dam and flows out. Now that's the conventional theory, which I don't buy that, and we'll get into why I don't. But let's keep moving on here. So here's a map of the terrain. So here's what's called Glacial Lake Missoula, right, at full pool, which is 4,200 feet above sea level. And here is the channel Scabland. And right here is the so-called ice dam. Now, right here at the snout of that ice dam is where Spokane is, and this is where the Cheney Palouse Scabland area here. The Telford is over here. You can see where it says Grand Coulee Dam, Dry Falls. I'm going to show you a picture of that in a minute. And right over here, this represents Moses Coulee right here, coming off the snout of the Okanagan Lobe. And this is the Columbia. And as you can see, it says the Columbia River's up here, but obviously when this ice was fully extended to the south. There was no Columbia River as we know it now. But what you did have was you had this massive discharge of water right over here that I think was not, and we're not going to have a chance to really break down all the details of because it's very complicated. It's extraordinarily interesting to get into it. But here's the general idea, is that you had this ice lobe here, and you had this big lake that formed behind it. Now, I said that the full pool elevation was 4,200 feet above sea level. Just to the west of the ice dam here, I'm sorry, just to the east of the ice dam here, the elevation of the ground is 2,100 feet above sea level. So do the difference, 2,100 feet to full pool, 4,200 feet, you're looking at a 2,100 foot hydraulic head against a tempered glacial dam, which I will state categorically I think is impossible. Yet that's the prevailing theory. We won't have time to get into this now, but I've done quite a bit of research into modern ice-dammed lakes, in other words, of the last 50 to 100 years. Remember yesterday I was talking about the Little Ice Age? Robert mentioned it in his talk. During that Little Ice Age, glaciers worldwide grew to the biggest they had been since the end of the Great Ice Age. Well, as a result of the warming that began in the early 18 to mid 1800s, they began to shrink back. Well, as they began to shrink back, a lot of meltwater lakes formed adjacent to the ice. Well, what we see then is that these lakes would sometimes catastrophically drain. The problem is those lakes would overwhelm the ice that was holding them in once they reached between 100 and 300 feet in depth, typically. And the volumes of water discharged in these modern ice-dammed lake drainages, typically only 1/10,000th of the peak discharges that we see right here. Yet, the geologists just extrapolate upwards and there's no problem. We just take this model of what we've seen in recent times and we just enlarge it by 3 orders of magnitude and we can explain what we're seeing here. And I say, guys, time out. We got to think this thing through. Because first of all, if you look at a water column 2,000 feet deep, you're looking at about 960 PSI at the base of the ice dam. There ain't no way. There's just no way. Those kind of pressures, you don't see anything. Look, what's the tallest dam in North America? It's Hoover Dam out there on the Colorado River, right? The hydraulic head behind it's about 500 feet, right? Now this is a steel reinforced dam with bedrock grouting. And why do they do bedrock grouting? That injects grout into every crack and hole and aperture in the bedrock beneath the dam, because you can't have a single little means of that water to move through, because it'll start out maybe it will create a catastrophe up here. I'm getting so excited here. It will create a leak that will percolate for a while, but then it'll begin to grow and it'll exponentially grow, and then you'll have a catastrophic outflow. And there's Ben, speaking of catastrophes. Hello, Ben. You just passing through? Looking for coal. Oh, okay, yep. There's probably some back there. That's Ben, by the way. Ben's a good man. I've traveled with, when you travel with somebody, that's when you get to know them. I've done several trips with Ben now. And we have the best old time. Okay, so let's keep moving here. So here's another variation. And you can see Glacial Lake Missoula in Montana. You can see that the ice dam is in the panhandle of Idaho. And you can see that the light blue is everywhere that the channel Scablands floods, all the land that it covered. Now, in the current models, this doesn't make sense. Why? Because to have the full terrain of the Scablands submerged, like it's implying here with it being blue, the reservoir of Glacial Lake Missoula would be empty, right? Now, in my scenario, this would be more accurate, because I'm maintaining that the reservoir of Lake Missoula was full at the same time the channel Scablands were completely submerged. So now, what I'm going to do here is we're going to see some photos from the ground and some from the air. And if we go right in this area, this basin right here, that's where the town of Missoula is. And right there along the outskirts of Missoula are two mountains, Mount Jumbo and Mount Sentinel. And on those mountains, you see this. You see the horizontal lines? They're called Strandlines, but what they actually are is shorelines. And the top shoreline is nearly 1,000 feet above the basin floor. So we can then gauge from that how deep the water was here. Now, to the west, against the ice dam, I'm using the terminology from the conventional terminology, just because it's convenient, right? So at the ice dam position, the water was 2,000 feet deep. But of course, now you move to the west, to the east a few hundred miles, the gradient has gone up. Even though the water level has stayed level at 4,200 feet, gradient has gone up 1,000 feet, right? So here, high water mark still 4,200 feet above sea level, but the floor of the valley is about 3,200 feet, where the town of Missoula now is. This picture here was taken, this is an old black and white one where you can actually, with the snow melting on it, it really brings out where you can really see the horizontal strand lines. Now, I mentioned the idea of scale invariance a little earlier, and I took this picture. This was on it, like it says here, this is current ripple sand deposit on the floodplain of the South Fork Peachtree Creek after Hurricane Ivan flooding, which I believe was 2004. The floodplain is now occupied by Medlock Park, and it's always a good idea to not put, houses and stuff on floodplains because they do flood, right? It had been decades since any flood had overtopped the modern banks of the creek, which are actually in that foliage. If I went 20 feet into that foliage, I'd be dropping down about 15 feet into the modern stream channel. So what had happened is there was so much rainfall because Hurricane Ivan came up and sort of stalled over North Georgia for a while, and it completely filled the channel of Peachtree Creek, and it overtopped the modern floodplain. And I was able to gauge how deep because you could see there was actually the clearest evidence was there was buildings that were on the park, and you could see the high water line very clearly on the side of the buildings, and the water was 2 feet deep. And after the water drained away, it left these current ripples here, right? So here you see this is evidence that there was water flow. This water flow has not been overtopped since then, right? So these ripples are obviously long gone. But you can kind of see there, it shows the chord length and amplitude of the ripples. Chord length, if you look carefully, you'll see is between 2 and 3 inches. Amplitude is about 3/4 of an inch. So you can gauge there, think of the size, the amplitude of these ripples, and the depth of the water. Now let's look at this. This is at Camas Prairie in western Montana. And this is called West Bar along the Columbia. Now in both cases here, you're looking at a series of, we're looking to the north, and we're looking at a gigantic ripple train. And these ripples are between 30 and 50 feet in height. That's the amplitude, with a chord length of between 200 and 300 feet. And then you can see there's actually a fan delta up here. I'm not going to explain every single terminology now, but this is a basin. It's about 5 miles wide. And you can see the shoreline, again, 4,200 feet above sea level. The water that came rushing through here from the north, right? And then there's actually a row of hills. You can't see it in this picture. In my more elaborate slideshow, I do have a lot more pictures, but I took this from the air and probably, about 1,000 feet up, I think, from the floor. So I'm not even actually in the airplane as high as the water was deep, because the water coming through here was 1,400 feet deep. So I want you to visualize in your mind, if you can, a river that's 5 miles wide, 1,400 feet deep, It's probably moving at 60 miles an hour, and it's choked with thousands of gigantic icebergs. That's what you would have seen here if you could have gone back in a time machine. You'd probably want to be in a UFO in high orbit looking at this. But that's what you would be witnessing here. So how do you explain all this? Well, and then this is West Bar. This is a 3 miles long, same scale of ripples. The water that came through here was about between 800 and 900 feet deep. This is on the Columbia River. This is one of our stops that we have a place we stop on the far side here where there's an overlook where you really get a beautiful view of this gigantic gravel bar, boulder bar, which is about 300 feet thick. It's a fossil feature because the forces that created it were so beyond anything that has occurred since then that the feature that it built is still there 12, 13, 14, whatever, 14,000 years later. The same with this one. This is a gigantic ripple train, we call it, and nothing is really, there's been no force of nature since the creation of this ripple train that has been able to erase it or disturb it or destroy it. It's still there because the forces subsequent to the creation of this have just been minuscule compared to the power of the force that created this ripple train, that created this one, and so on. And it says, note 3-story building for scale. Let's see if we can, the 3-story building is right there. There's a little white building there. Let's go to the next one. So this is from the overlook. And if you look very closely right here for scale, you'll see a little guy standing right there. Okay, so now one of the other diagnostics for these giant floods is this. As I just said, there are thousands of icebergs being carried in this flood water. Many of these icebergs have rocks in them, boulders, and sometimes these boulders are really big, right? Now, if you look at this is along the Columbia. You can see there's a boulder here. You can see there's another one here. They're up here. You can see they're all the way up here to the top of the hills, almost 2,000 feet higher up, right? There they are, and you see this rock. Now, when I took this picture, a couple of buddies of mine were standing right in the front of here, and I just took them out just because I wanted you to take in the whole scene first. And then what we'll do is we're going to, oops, darn, the slide is missing. Okay, well, there's a couple of little midgets standing there in front of the rock that you can see, but I've got more. I think you'll get the idea. This is the scenario here, and this was, interestingly, this was what was his name? Rio. I forget the artist's name. He did the illustrations for this book, a geology book published in 1872 by Louis Figuier. And this was in a chapter called Deluge. And he was still a catastrophist geologist, and he was looking in Europe. And he saw similar evidence there, and this was the scenario showing huge flows of water. And in some of these, they're carrying icebergs. Some of these icebergs have huge boulders on them. Here we go. Okay, we just got a little bit out of order. Okay, so here it says this giant deposited by melting iceberg that was stranded on the hillside is found near the mouth of McNeil Canyon along the Columbia River. Now let me put my buddies in there so you can really get a sense of the scale. So this rock was carried aboard an iceberg. The iceberg stranded on the hillside. And then probably over years it took for that iceberg to melt. And as it melted, essentially the final act of putting this rock in place was actually pretty gentle because it's sitting on an iceberg. The iceberg is melting, and then the rock sits down and then strands on the landscape on this ridge here, and nothing has moved it since. And there's like a 15,000-ton behemoth sitting 400 feet above the river. Again, same process. This is being carried. This is a gigantic basalt boulder ripped ripped out of the walls of basalt north of here. When this water gushed out and hit the rim of the basalt plateau, whammo, it just is gouging up thousands of these huge boulders of rocks. Some of them end up on the icebergs that are being carried in that floodwater. When those icebergs are swept down, sometimes as the water levels begin to drop, the icebergs get stranded on the ridges, on the hilltops, and the ones that have the big boulders above on them, they will melt, and then there's the consequence. So try to imagine, you're looking at this boulder. The size of the iceberg that's carrying this boulder is probably like a tanker ship. Now, imagine the flow of water that's floating an iceberg of that size, and you start to get the impression. As you go across what's called the Waterville Plateau, you begin to see things like this scattered for as far as the eye can see, gigantic boulders. This is called Jaeger Rock. It sort of marks the very beginning of the downcutting of Moses Coulee. We're looking to the east here, so south is to the west. You can see there's another large boulder here. You can see there's a large boulder over here. When you get up to the Jaeger Rock itself, it's like that. And it sits in a berg mound. A berg mound is when you have an iceberg, the glacial ice is dirty. It's filled with gravel, rocks, boulders, dirt. So when an iceberg like that melts, it leaves a mound of debris. Makes sense, right? So you have here a gigantic erratic boulder of basalt sitting in a berg mound. Now there's lots and lots of berg mounds without big boulders in them. And once you learn to recognize a berg mound, you go, okay, there was an iceberg there. And so that's one of the paleocurrent indicators. There's a whole set of these diagnostic features that if you're tracking the route of one of these floods, there's things you look for, right? One of them is, okay, we know that there were icebergs because the whatever the force that caused this water, like what was the source of this water? Well, in the conventional models, it's just the Lake Missoula gradually fills over 50 to 100 years. And I'd reject that idea. I don't think the Lake Missoula was even a lake. I think it was just a gigantic temporary backflood holding pond, right? And I have amassed an enormous amount of evidence that I think supports that. And I've done multiple traverses all throughout the valleys of Lake Missoula. And anyways, then of course it raises the question of what was the source? Well, I think the source, if you want to look at the geographic source, not the cause, but the source, you have to go all the way north to British Columbia to an area called the Nechako Plateau, up there near Prince George. So I would highly recommend, if you're really interested in this, go to Google Earth or Google Maps. Google Maps, go to Terrain View, and you can trace these north-south trending valleys. They converge right on the Nechako Plateau, it's called, and Prince George is right there. And I think that is where the floods emanated, not from Lake Missoula. And that's one of the major differences between my thinking and the conventional models, is the conventional models go to Lake Missoula and they say this was the source of the floods. And I say, no. The floods actually came from the north. And it's actually the opinion, scientific opinion, is beginning to shift now. In fact, it showed up, Nick Zentner, who does really nice job of doing videos about all of this. He had a meeting, maybe a couple of meetings with Jerome Lessman not too long ago. And Jerome Lessman, I've been out in the field with him a couple of times. He's been on Cosmographia podcast. He was a student of John Shaw. Now there's a whole backstory there we need to get into. John Shaw was the guy who studied these gigantic drumlin swarms. And I don't know if we're going to have time to get into what drumlins are today, but I'm going to be trying to put this out on my new podcast to try to break it down into digestible chunks. It maybe take me half a dozen or 10 episodes to cover all of this, but I would highly encourage you that when I start getting it out there to look at it and to learn about this, because I think that this phenomena goes way beyond what the conventional thinking permits. So we'll just look at some pictures. This is, as you travel over the terrain, this is my buddy Brad up here, just for scale. Nice color overview of upper and lower Grand Coulee, which is right here. Oftentimes when we do the Scablands, we've made good friends with the owners of the Soap Lake Resort, which is right down here. And they kind of roll out the red carpet for us, and we stay there and we use that as our base, and we go out for day trips. Pat Dahmer has been on a bunch of these trips with us. He's one of the stalwarts who's helping to make these trips possible by his contributions. And what is your impression of what you've seen so far, Pat? I think we're getting close to time to break for lunch, so I'll just show you a few quick little graphics here so you can see the relationship of the lobe itself and the moraine. And you can see the moraine is very distinct. Moraine is the feature, the material composing the feature is called till, T-I-L-L, or glacial till. And then you can see that Moses Coulee actually begins up under the ice sheet. Whoops. See that? Now, I read several times the Larry Hansen, who was a geologist who did his doctoral dissertation on Moses Coulee in 1970 it was published. And he said that he didn't think that Moses Coulee was coming from Lake Missoula. He thought it came from the north. But his opinion on that was for the most part completely ignored. But now his interpretation is being vindicated. This is just some of the erosional features. This is that dog leg. So Moses Coulee comes down here, it hits this anticlinal mountain ridge and gets diverted to the west, and then it dog legs down here. And you can see that when you look at this, you'll see that the Coulee just ignores the pre-existing drainage pattern. And you see this hummocky terrain in here. And here's where Moses Coulee meets the Columbia, and this was two gigantic flows that came together right here. And this point, think of it like as the prow of a ship, okay? Let's see if I've got some aerials of this. Yeah, so imagine that we're in an airplane right down here, and we're looking up this way, and we're looking up this way. And that's what we're seeing here. And so we're seeing a Coulee, Moses Coulee up on the right, up here, and then the Columbia River here, and you'll notice the sheer walls, and then there's huge gravel deposits, boulder deposits, flanking the bottom of these. This is not normal talus emplaced by gravity. This is wash-up material that was being carried in the floods, and when the floodwaters subsided, they washed this stuff up against the cliff walls, okay? These walls are between 800 and 900 feet high. There's like 300 feet of sediment on the floor of Moses Coulee. And if we were to clean that out, the Coulee would actually be closer to 1,200 feet deep. Here's another view of the same. And you can see here how thick this sediment layer is. It comes out of Moses Coulee and then it splays out across the Columbia Valley. And the modern Columbia River has incised a channel. And here you can see the truncated hills. And the waters of Moses Coulee completely ignored the pre-existing drainage. They just sliced right across it. And of course, what happens now is that during rainfalls, you have channels of water coming down these troughs, and they form waterfalls. And we're just going to speed through a few things here. Yeah, here's Camas Prairie. So this is where I said visualize the river 5 miles wide and 1,400 feet deep. We're up at a level here. We're still not above the water level where we took this picture, but we're looking out across. We're looking to the west here, and that blue line represents 4,200 feet above sea level. And there you can see, you know, this is like thousands of people will drive down these roads. They will not notice, or if they do, they don't know what they're really looking at. But now you know, these are shorelines. These are fossil shorelines. And this is the Clark Fork River, and this is Lake Pend d'Oreille up here, and somewhere right in here is where the supposed ice dam was. Right now, I do believe that there was ice filling this valley here, but I don't think it formed a dam. I think it was basically just a temporary impediment to the flowing water, which quickly washed it away. And in here you can see, let's see if I got it, yeah. So as we travel through the Clark Fork River, we can see that high water line at 4,200 feet. You see the transition from basically bare rock to where it's still forested. That represents the high water mark. But to give you a little bit of perspective on this, let's see, like look at the little figure down here, and the water moved from right to left, and I want you to look at the texture of that rock, because these are the kinds of things you learn to look at. And that is rock that has been subjected to extreme shear pressures of flowing water, probably moving 50 miles plus per hour, literally scouring the surface of the rock. And so on this one, I don't know if you can see it very well, I've got two transects. Well, one of them is right here, where the valley, while the valley is still constricted, and then there's another one right here where it opens into the basin. So what I've done is I've taken that cross-section profile, like right here, and here's the water level at 4,200 feet. Here's the bottom of the valley floor. As it says here, a southwest to northeast transect through the basin of the Cabinet Gorge Reservoir, about 3 miles west of Cabinet Gorge, which is a place we usually stop at. There's a modern dam there overlooked. It's a great perspective. And now what I'm going to do is I think I've used the profile of the skyline of Atlanta that I put in there, but it could be the tallest building in Atlanta is about 1,150 feet tall. It's a Bank of America building, right? And I could put any city in there. I could put New York, I could put Detroit, I could put Chicago, I could put Washington. It doesn't matter. It's about the same. So there's the skyline of Atlanta. So you can see we're not talking about any kinds of floods similar to anything that's happened in recent years. And here, yeah, so here's just another version. That's skyline of Atlanta, and that would be the depth of the flood as it's moving through the Clark Fork Valley. So here's a point that I want to make, is that if by some fluke you were able to witness an event like this and survive, well, I mean, you would easily be, for those of you that were here yesterday and I talked about the Tunguska event spawned a new religion, and that they believed that this was the visitation of the god Agni from the heavens who came down to punish them for their transgressions. Well, can you also imagine how in the aftermath of a flood on this kind of scale would leave survivors thinking very similar kinds of things? Now, what I'm showing you here is some of the most spectacular flood evidence on Earth. However, once you learn to recognize it, there have been gigantic floods over the entire planet, okay? There are features in Northern Europe that were produced by gigantic floods, almost this big. There are features in Russia, Mongolia, Siberia, almost the same in the Altai Mountains where China, Siberia, which is Russia, and Mongolia come together, the Altai Mountains. There are floods that are at least the same scale as what we're seeing right here. Recent studies, some really great studies were coming out of Russia on their giant floods. Of course, all of that is stopped now with this Cold War bullshit. So now all of the scientific communication has been mostly cut off and terminated. So all the things we were learning about there from their astronomers about impacts and asteroids and comets and the Tunguska event, that's all cut off now. The floods and all of that, our scientists are not communicating anymore on that. So there's so many downsides to this foreign policy that I don't mean to get off on that, but it's crazy. anyways, you can see here these features. These were islands. There's a term here called that describes these. It's a scientific term. It's streamlined erosional residuals. All right, streamlined erosional residuals. Write that down. Learn it. You can use it you can pull it out when you want to impress your friends, because that's important, right? Impressing your friends. You can add that to paleocurrent indicators, right? Paleocurrent indicators, anything that you can use to determine the flow of an ancient current that is no longer operational. So when you look at one of these, like when you look at one of these features right here, from the ground, they look like this. That's a hill. It's about 200 feet thick. The thing to appreciate here is that pre-flood, this was the land surface up here. Now, post-flood, this is just an island, right? 200 foot thick of topsoil. So here is a typical gravel bar on that same creek that I showed you before, Peachtree Creek. And basically, here's another one, a giant gravel bar in the Snake River. And it's miles long, hundreds of feet thick, but it's basically the same thing as you're seeing right there, just a gigantic version of it. Here's another one. Now see, these are things like people come every day, you're driving across this bridge and going on this highway. No concept of what the secrets, the story that this landscape is concealing and revealing and preserving.